And so without further ado, let's actually leave our planet Earth and go for a little adventure to the third biggest galaxy in our local cluster. Now, the most famous galaxy that is not Milky Way is Andromeda. You've all probably heard about it, you've all probably maybe even seen it. In the skies, it's very visible if you are in a location that has very dark skies. And it's basically the largest object that we have in our dark skies, and at the same time, one of the farthest objects you can see. I'm going to show you where it is located in Space Engine by basically leaving our galaxy, the Milky Way, pointing at Earth by doing the following. So there's Earth right there. And now we're going to look for Andromeda. And so if I just turn a little bit to the left here, you'll notice that right there is an object that seems to be galactic in shape, and that's Andromeda. But today we're going to be talking about the third large galaxy in our local group of galaxies that has about 60 various galaxies to begin with. This object is right here, and it's known as Triangulum. It's kind of in the same direction as the Andromeda Galaxy, but it is significantly smaller. So as a matter of fact, if I actually use my binocular function here, so there is the Andromeda Galaxy, this is what it looks like, and there is the Triangulum. Now, what is so interesting about Triangulum? Well, first of all, it's not as well known. As a matter of fact, if you're a gamer, you might have actually only heard about it once. It only appeared in one game I can think of, in the game Crisis that came out in 2007. The aliens were actually from this galaxy right here. The Ceph were from Triangulum. But that's the only reference I actually can think of to this galaxy. And it's not that we don't think it's important. It's actually just as important as Andromeda. But for some reason, it's not as popular. Anyway, we're going to go to it right now, and we're going to explore it in a little bit more detail, starting with its structure. So this is about 2.8 million light years away from us. In other words, the light from this galaxy takes about 2.8 million light years to reach us. In terms of size, it's about only maybe 40% of mass of the Milky Way, and it only has about 40 billion stars compared to about 400 billion in our own galaxy. Its diameter from end to end is about 60,000 light years, so this is about half of what our own Milky Way is. And in terms of the actual visible mass versus dark matter, about 20% is so-called baryonic matter, so basically visible matter. And the rest, which is about 5 times 10 to the power of 10 masses of sun, is the invisible dark matter. Now, what's interesting about this galaxy is that it is essentially a spiral galaxy similar to our own Milky Way and similar to the Andromeda Galaxy, which is right there and visible quite clearly from Triangulum. But unlike Milky Way, this particular galaxy is classified as just spiral galaxy without an actual bar in the middle. If I were to go back to the Milky Way and to look at it from, I guess, this angle here, you could kind of see that there's actually this bar-like structure in the middle that actually classifies our galaxy as a bar spiral galaxy. Whereas the Triangulum Galaxy doesn't have that, so it's called just spiral galaxy without the bar part. Now, you may notice that one of the main differences between the Milky Way and this is that it has a lot more of these bright spots everywhere. And as a matter of fact, there's at least like 515 various really bright spots like this here and this there. So in other words, nebula or supernova or possible star formation regions that are really, really prevalent in this particular galaxy. Interestingly, just from observations and comparing this to Andromeda Galaxy, we know that in this particular galaxy, there's like 4 times more stars that are being formed at any moment than in the Andromeda Galaxy. So even though this is actually smaller by mass, it's a lot more active in producing more stars, which is why it has these really bright spots everywhere that you can see, especially this one right here that's very, very bright, very visible, and has actually quite a lot of interesting stuff in it. And let's actually maybe visit this for a second, just so we can see what it looks like in more detail. And this is known as NGC 604. It's a very interesting looking nebula. As you can kind of see, there's a bit of a cube here in its shape, and it looks absolutely incredibly gorgeous. Now, what's really interesting about this galaxy is that it was actually discovered a long time ago. As a matter of fact, the first person to discover it was an Italian astronomer by the name of Giovanni Hodierna, and he discovered this sometime in mid-1600s. Then about 100 years later, this was classified as a kind of a nebula by Charles Messier, who was the French astronomer and is famous for the Messier catalog, which is why this galaxy is also known as M33. So if I were actually if I click on the galaxy, you'll see that it's going to be listed as M33 right here. That's because it's the 33rd object that he listed in his catalog. And sometimes this is also erroneously called the Pinwheel Galaxy, although in reality, Pinwheel Galaxy is actually something a little bit different. It's the galaxy known as M101, and it's located right around there. So that's actually the Pinwheel Galaxy, and this is the Triangulum Galaxy. And the name Triangulum actually comes from the constellation where you can discover this galaxy, which is also known as Triangulum. Once again, because this used to be known as a nebula, before we identified this as a galaxy, we actually thought that this was a nebula in the constellation Triangulum. Now, there's another really cool feature that we discovered about this galaxy, and that's actually the interaction between Triangulum and the Andromeda Galaxy. We've discovered that they actually are connected to each other through various streams of hydrogen, but also through a very thin pathway of stars that's kind of invisible in this game, but it is there. So there's actually a path of stars that connects them, which suggests that a long time ago, maybe 2 or possibly even 8 billion years ago, these two galaxies came really close together and they actually interacted with one another. And this also means that in about 2 to maybe 3 billion years, Triangulum will once again approach Andromeda and will either get absorbed into it or possibly, which is very likely, will actually get absorbed into the union of our own galaxy, the Milky Way, and the Andromeda Galaxy, because we know for a fact that Andromeda will one day collide with the Milky Way and will create what we sometimes call as Milkdromeda. And so maybe, just maybe, this galaxy right here, known as the Triangulum Galaxy, will actually join the union as well, and so maybe, just maybe, we'll have to call them the Milkdrogallum Galaxy? I don't know, maybe you have a better name, post it in the comments below. But anyway, so yes, it's a pretty exciting galaxy, a lot of new stars are formed here, a lot of really cool things going on, and this is actually the location where we've discovered some really cool things. Like, for example, there, one of the only objects listed in Space Engine is known as M33 X-7. Now, this is actually a location for one of the most massive stars, which is what we see right here, but also a location for a very interesting binary system. This is also known as a binary X-ray variable because, and let me just maybe dim this a little bit so you can see it better, because this is actually a binary object. This is a huge Wolf-Rayet star, very, very massive star that's going to explode one day and create a tremendously powerful supernova. Very bright, very massive, and that will probably lead to creation of new stars. But what's orbiting around it is even more interesting. This right there is actually the biggest solar mass black hole we've discovered. In other words, it's the biggest small black hole we've discovered. It's about 16 masses of our own sun, and it orbits around this supermassive star known as M33 X-7. And there's actually the black hole. I'm going to slow down time just so you can actually see what it all looks like as it orbits around its companion, the supermassive Wolf-Rayet star. Now, if you don't know what Wolf-Rayet stars are, check out the video I made a few months ago about them. And if you want to check out more black hole videos, they're also available for you as well. But anyway, so this is actually a very unusual object, and we don't really understand how they were formed because both of these are super massive. This is 16 times mass of Sun, and this one is about 70 masses of the Sun. And we think that they were created together, but what probably happened was that this star must have had a humongous supernova, and this one will have an even bigger one. So both of these stars will probably create some kind of a binary black hole at the end. But anyway, so that's just one of the exciting things we discovered here. And using all of these discoveries, including this black hole and this supermassive star, and the fact that there are so many new stars that are formed in Triangulum Galaxy, this actually allows us to study the universe itself, because this is a nutshell of how things interact in the universe and how things are formed. And because this galaxy is much smaller than Andromeda and a lot more active, it's actually a really, really good opportunity for astronomers to study how things in other galaxies are actually formed and how they interact, because this is pretty close to us, it's very, very bright, it's very visible, and it has so much activity going on in there. But obviously we still have so many mysteries about this galaxy, and we still haven't really discovered everything about it, and there's still so much more to find for us by looking and studying this incredible spiral galaxy. Now we're actually going to go and find the supermassive black hole in the middle of this galaxy, and we're going to try to do this manually. But at the same time, that's pretty much it I wanted to cover in this video, and I wanted to kind of give you an idea of what we know and what we discovered so far, and why this particular galaxy is definitely worth more time to study. Now I wonder if this supermassive black hole is going to be in this globular cluster, or if it's going to be somewhere else. Now I'm going to take a chance and jump into it and see if I can actually find it using my manual navigation skills here. And hopefully one day, maybe in the future, might be able to even visit it in real life. Now, interestingly, the only other thing we know about this galaxy is that it's approaching Andromeda Galaxy at the speed of about 200 kilometers per second, while Andromeda Galaxy is actually approaching us. So what we still are not sure about is what actually happens to Triangulum Galaxy in the future. There's several possibilities. One of them is, of course, joining with Andromeda and the Milky Way, but it's also kind of possible that this galaxy might be actually thrown away out of the local cluster because of the interaction with the Milky Way and the Andromeda Galaxy. It's somewhat possible that it actually might disappear completely, well, not disappear completely, but get thrown out into the outer clusters and possibly join some other galaxies somewhere else. Now, I'm very, very close to discovering the supermassive black hole, and I know it's going to uncover itself any second now, because that's usually how this works in this game. So we're going to come really, really close to the location where it possibly is located, and maybe accelerate time a little bit just to see if any of these stars here start acting a little bit unusual. And look at that, here you go. There is that supermassive black hole with lots and lots of stars moving around it. And this is how you can discover all of these supermassive black holes there. Now they kind of stopped moving because I made time into real time, but if I were to accelerate time again, you would see that they would be spinning around this invisible object somewhere in the middle. And this is how you can locate where that supermassive black hole is, and this is essentially how we located our own supermassive black hole, Sagittarius A star. And there it is. You see that one object that's not moving anywhere? That's gotta be that supermassive black hole. And in this particular simulation, it's listed as 50,000 masses of our star, the Sun. And so let's approach it a little bit closer and take a look at it, and then maybe leave the system, fly away, and go back home to our own planet Earth. And so there you go, there's that supermassive black hole of Triangulum Galaxy. Anyway, let's return home, take a look at Triangulum Galaxy from the outside once again, give it the last look, enjoy its beauty, and return to our planet Earth. So a few billion years in the future, the Milky Way galaxy and the Andromeda galaxy will actually most likely collide.
And when this happens, there's a slight chance that instead of the two supermassive black holes at our center, or basically in their center, combining into one, there is a chance that one of them will actually get kicked out of the system. And let me actually see if I can do it right now. We're going to try to change its velocity just a little bit to make this slightly more realistic, and see if we can actually make it happen. And when this happens, and I actually was able to recreate this in one of the previous simulations where I did it completely by accident. It was actually a simulation where I used Elon Musk's Tesla and turned it into a black hole. And it just so happens that it kicked out the black hole from the center. And when the black hole got kicked out, it actually took a few stars with it and created what's known as a hypercompact stellar system. Now, obviously, when galaxies collide, sometimes they actually combine each other's black holes and become one. There's a chance that Milky Way and Andromeda will do the same. But we've actually observed galaxies that have no black holes, suggesting that two galaxies collided and the black hole basically ran away, flew away, and escaped, and created its own system, which we're going to try to do again. Far, far, far away. So, okay, it's maybe not moving fast enough. I need to give it a little bit more velocity just so it moves faster. Let's give it maybe 2,000 kilometers per second. That should be enough. Now, what actually makes this sort of object different from, let's say, globular clusters? Well, for one, the stars moving around the hypercompact stellar system, also known as HCSS, is usually a type of a system where all of the stars move really fast. A globular cluster will have stars moving around it really slow, but here all of the stars move at like thousands or at least a few hundred kilometers per second. The other thing that makes this a little bit different from a typical object is that it's very massive. So a globular cluster would not really be that massive, but this, which is now technically a hypercompact stellar system, is ridiculously massive because of the black hole. And the stars here only represent about maybe like 1% of the mass, whereas the supermassive black hole is most of the mass. And so from a distance, it actually kind of looks like a very unusual, very weird dwarf galaxy or a globular cluster where everything moves really fast and there seems to be a lot of ridiculous mass. So there's actually a few of these we've discovered that we kind of suspect are these types of objects, also simply based on the amount of energy produced by the supermassive black hole. But we do think that this is kind of what may actually happen, or there's a chance that it may happen to our solar system, or not our solar system, but our galaxy, that is, the Milky Way. So there's a slight chance that the Milky Way black hole, also known as Sagittarius A star, which I believe this is actually, I think this is Sagittarius A star, might actually get kicked out of the galaxy and end up becoming this, which is HCSS. And interestingly, even though it gets kicked out of the galaxy, it still kind of remains in the same galactic cluster, meaning that it will probably even become a satellite of its own previous galaxy, and maybe at some point will escape further, but it will still be gravitationally tied to other galaxies that might be in the neighborhood. So, like for example, we can actually try to see if there's a smaller galaxy we can add. So kind of like this, I guess. Let's maybe make it binary. And so you will still have this cluster, also known as hypercompact stellar system, kind of orbiting in this vicinity. Okay, that actually unfortunately broke it apart. That's not what I expected to do. Well, anyway, so let's see if we can maybe create another one using. Well, no, let's use the same simulation. So we're gonna go with this simulation here, and take the supermassive black hole, give it some velocity as it moves across the skies, maybe 3,000 kilometers per second, and let's see if we can create it again. Normally it's a little bit more difficult to create these because they're a little bit more unpredictable, but did we do it? Okay, something came out on the other side. You can see the black hole actually shot through the galaxy here, and I think I made it again. It might be in this vicinity. Let's check it out. Oh, there it is. Look at that, beautiful. I think I succeeded. Yeah, there it is. There's a black hole, and this is the new HCSS. So the thing about these particular objects is that we don't really know of actual examples just yet. So this is still kind of theoretical. We do have some suspicions about some of these objects being HCSSs, but we haven't really discovered them. But it's been estimated that nearby Fornax and Virgo galaxy clusters may contain hundreds or even thousands of these. So they're actually suspected to be quite common. They have been a lot of different clusters detected over the past few decades, and it's possible that we actually misidentified some of the globular clusters and some of the dwarf galaxies, which were in reality this thing. So it's possible that we need to reclassify these a little bit, because it's actually quite easy to find and quite easy to distinguish them by looking at them for a little bit longer than a few days, and you can kind of see that the speed around these things will be much higher than the speed around a typical globular cluster. So it's really about the compactness and the velocity of stars here. And also these will most likely produce a lot more flares, and they'll produce a lot more energy, because stars here will probably approach the black holes, or the black hole in the middle, a lot more often. And so there will be a lot more outbursts of energy, and most importantly, a lot more different types of supernova. And the stars here would most likely be iron rich and very young. And so if we actually investigate a lot of globular clusters we discovered, we might find quite a few of these HCSS objects. And if we actually find one of these objects in real life, we'll most likely be able to then investigate and basically prove that, first of all, supermassive black holes may exist outside of the galaxies. Also, they'll help us predict gravitational waves a little bit more, and not just predict, but analyze gravitational waves a little bit more. And this would also imply that not all galaxies have supermassive black holes in their center, because some of them may have lost them over time. We have a few suspicions about a few galaxies, but we haven't really been able to prove it just yet. If we discover these with binary black holes or other unusual types of formations inside, this will help us understand how the universe evolved over time, and obviously help us understand how our galaxy was born and how we were created as well.
Hello wonderful person, this is Anton, and today we're going to be talking about galaxies, and specifically the Andromeda galaxy, and a more recent study that seems to actually indicate that Andromeda might actually be very, very young, even younger than our own Earth. Let's talk about this, and welcome to What the Math. So right now we're looking at the Milky Way galaxy. This is our beautiful home, and our planet Earth is somewhere over here. But if we move at a distance of about 2.5 million light years away from our own system, we'll reach another galaxy. A very famous galaxy known as the Andromeda. Now, in some of the previous videos, I've talked about how one day our beautiful Milky Way and the Andromeda will most likely collide and create one super galaxy, for which we don't really have a name yet, but some people suggested calling it Milkdromeda might actually be appropriate. But what we actually just recently discovered, or not really discovered, but one of the papers basically speculated about and makes a really strong point, is that this beautiful galaxy is actually a lot younger than we thought. As a matter of fact, it seems to be only maybe 2 to 3 billion years old. Our Earth, in comparison, is close to 5 billion years old. In other words, this right here is about 1.5 billion years younger. Now, how and why and what did we discover? Well, first of all, this is actually a paper by a joint French and Chinese researchers that used a lot of data and a lot of computers at Paris Observatory. And so what they did here was analyze close to about 2 million photos of Andromeda Galaxy and use a supercomputer to simulate various collisions and try to basically explain a few unusual features in the Andromeda. Now, we unfortunately don't really have all of those features, and it's kind of difficult for them to be simulated in Space Engine, but I'm going to try to point them out to you. first feature that they tried to explain with these collisions was the fact that if you were to actually go into the center of the Andromeda Galaxy, and if you were to look at various stars in this region, you would actually discover quite a lot of relatively young stars that were approximately 2 billion years old. And these stars, with almost no exceptions, seem to be moving erratically all over the place, up and down, left and right. They basically kind of circulate pretty much hectically around the central region. Now, if you were to do the same to our own Milky Way, if you were to go back to the Milky Way, which is somewhere over there, and to basically look at the Milky Way galaxy, you will discover that our relatively large and young stars move very orderly in a circular motion. They don't move up and down almost at all. In other words, they orbit the central region more orderly, whereas in Andromeda they are all over the place. This is one of the first hints suggesting that maybe, just maybe, there was some sort of a collision that created a very large dust cloud in the center that probably created all of these young stars that we have there. And just the fact that there was so much dust here to begin with to create all of these very young stars is actually a very clear indication that there might have been a collision very recently. So this dust that suddenly accumulated in the center and created these young stars must have come from somewhere. There is another very unusual part of Andromeda that we could never explain. And for this, I'm actually going to take us to Google and to basically this paper from December of 2015 that talks about the so-called giant stream. This is basically what you see right here. This is various large constellations or large, almost globular cluster-like formations that seem to be sticking out here and here in the halo of Andromeda. And it actually has a few of these. Now, what's interesting is if you actually look up giant stream on Google, there's already a lot of speculation that these were formed from a collision of two galaxies. And for this reason, I'm going to take us to the YouTube channel by the Observatory of Paris, where they actually released these two really amazing videos that I'm going to show you right here, simulating the collision and how they were able to explain both the formation of these unusual streams and also other features of Andromeda Galaxy. So we actually have several passages here where Andromeda had these two galaxies, and let me actually just go back a little bit to show you what they are. These two galaxies, one of which was about 4 times smaller in mass than the other, passing by each other about 7 billion years ago from now. And then 4 billion years later, they came back and essentially merged together. Now, this merger occurred at least 2 billion years ago. And this is where the thick disk formed that actually has both the halo and these unusual features known as streams. And specifically here, the giant stream is the one that we're particularly interested in. Now, notice how this simulation creates the Andromeda almost exactly as it is in real life. This is the picture of real Andromeda. This is the simulation. If you actually look at the second video they made, oh, and by the way, this is the name of the actual paper and the credits of people who were responsible for making this. But let's actually take a look at the second video that shows a little bit more detail about the actual merger, which is very, very, very interesting. So here, after the actual merger occurred, what you can kind of see is this is where that second tidal tail is created, which leads to those streams that I mentioned. And this is something that we couldn't really explain before. We thought it was from a collision, but we didn't realize it was from a collision relatively recently and from two large galaxies, because this was the question we were asking ourselves before. Did Andromeda form from a collision of smaller galaxies, or was it one or two big collisions from larger galaxies? And this particular paper that used the supercomputer to simulate all this stuff does explain a lot of the features that we see in Andromeda with the collisions of two relatively large galaxies, one being about 4 times more massive than the other. Now, here, this is where the giant stream is formed, and we actually are able to explain it using these simulations very, very well. And notice how pretty much every single part of Andromeda can be explained with this particular simulation, and this is actually something that I was really surprised to read in the paper. Well, anyway, so that's kind of what I wanted to talk about in this particular video. And in essence, I just wanted to basically explore the idea of Andromeda most likely being a relatively young galaxy, and when it actually collides with the Milky Way galaxy in about 2.5 billion years from now, it will create a much larger galaxy. But interestingly, in comparison to the Milky Way, Andromeda seems to be a relatively young creation. And it will actually be only about the age of our planet Earth, current age of planet Earth, so basically about 5 billion years, when it disappears and merges with the Milky Way. So there is the Milky Way, our beautiful galaxy that's also known as the Spiral Galaxy. And here we can kind of see the beautiful arms of the Spiral Galaxy, we can see the center as well. Now this is actually something that doesn't really happen very often. As a matter of fact, very few galaxies in our universe have these. The only other one that's kind of close to us is, of course, the Andromeda Galaxy. And the Andromeda Galaxy is right here at a distance of about 2.5 million light years from us. Now, these unusual galaxies are actually relatively old. As a matter of fact, they are some of the oldest galaxies in our universe, but how they formed and why they have this peculiar shape is still a mystery, because the majority of galaxies are usually like this one. They have this type of shape. In other words, they are what's known as an elliptical galaxy. This particular elliptical galaxy, also known as M1110 or NGC 205, is the partner dwarf galaxy orbiting around Andromeda. So most of the galaxies actually usually look like this. And as a matter of fact, all of the early galaxies have this shape. These spiral galaxies are very common pretty much everywhere. As a matter of fact, the biggest galaxy in our universe, and I can't believe I used the word galaxy like 100 times already. But anyway, the biggest galaxy in our universe is this one right here, IC 1101. I've talked about it in one of the previous videos. This one is tremendously huge, and as you can see, it also has the same shape. So what is it that actually creates those very unusual spiral galaxies? Well, we still kind of don't really know, but we think that the spiral galaxies are actually formed through the collision and essentially the combination of many of these beautiful creations. Now this one here has trillions and trillions of stars on the inside. So if I actually try to fly through it, you'll see how tremendously populated it becomes in a few seconds. There you go. So you can kind of see stars already appearing. And if you actually are in the middle of this galaxy, you probably wouldn't even see the outside. That's how populated it is. It'd be very difficult for us to see through all of these stars around us and all of the gas around us as well. But today we're actually briefly talking about the evolution of galaxies, and we're going to try to create this in Universe Sandbox. And so what we're going to do in Universe Sandbox is we're going to try to place a bunch of these so-called elliptical galaxies and then have them interact and then see what happens. Because according to science, the oldest galaxy we've discovered, also known as A1689b11, is actually one of these spiral galaxies that was formed in such way. And so using the Hubble telescope, the scientists from Australian Swinburne University were looking at various objects at a very far distance of about 11 billion light years away from us, and they discovered this tiny object right there. This object is known as A1689b11, and it was discovered in November of 2017. This object is essentially a galaxy that pretty much looks like our own, but the only difference is that this picture that we saw is about 11 billion years old. In other words, this seems to be the oldest spiral galaxy that we've discovered so far. Because of course, by the time the light traveled to our planet Earth, it was already about 11 billion years old. Now, this is interesting because we didn't realize these galaxies were formed so quickly after the creation of the universe. So in other words, about 2 billion years later, we already had galaxies that looked like our own. Now today we still don't completely understand how these are formed. As a matter of fact, the best theories we have about the creation of galaxies kind of look like this. Basically, they all start with elliptical galaxies, of which we have many, many examples, and then some of them become the spiral galaxies, and some of them become different types of spiral galaxies. And all of them seem to have relatively similar shapes, but they kind of end up as this. Now this is according to Edwin Hubble back in the days, and we still haven't really changed this theory very much. And this is kind of what we believe still happens to most galaxies. So the way that this one was formed was essentially as follows. And so what we're going to do now is we're going to take a couple of galaxies. Let's just take these ones because they do kind of look elliptical, and place them relatively close to one another, and then see what actually happens. Will they form something that looks spiral-like, or will they form something completely different? Now this is obviously not a very accurate simulation, but the thing is, if you place more than 2 galaxies in Universe Sandbox, unfortunately things actually become very, very hectic. So we will need to do this really slowly first. Let's start by accelerating time, making sure that time runs a lot faster than it was before, maybe even several million years per second. And then we're going to see how or what we can create using these two relatively elliptical looking galaxies. So if everything goes right, we'll have something a little bit more flat than this, and if not, then we won't. And as you can see, at the speed of about several million years per second, things start moving around. Galaxies seem to be joining together, but we might need to wait a while before they actually come close enough together for us to see any effect here. Now, first thing you may have noticed here is that the two supermassive black holes at the center of each of the galaxies have not actually collided. And one of the reasons for that is because they're not really flying directly toward each other. As a matter of fact, the material around them and the dark matter around them does influence their trajectory. So when several galaxies come together, their supermassive black holes might end up actually being inside of the central region, but not combined with the actual black hole in the middle. On the other hand, because they start orbiting around one another now, they're going to be creating quite a lot of disturbances in the central region, but also on the outskirts. And this is kind of similar to how binary stars usually have trouble keeping some of the objects in orbit. And so for a planet to orbit a binary star, it needs to either be very close to the central star, or it needs to be kind of on the region that's very far away from both stars. Now in this case, it seems that these two supermassive black holes are very, very close to each other, and so they're going to be creating some very interesting effects here. One of these effects is probably going to create occasional gaps in the central region, but also on the outskirts. These gaps will be basically formed because these two black holes are circling around one another and are creating a barycenter that's going to be moving around and disturbing orbits of other stars. So some stars might actually escape this galaxy now and end up somewhere else, and some stars might end up coming closer and closer. So in other words, this will reshape the shapes of these galaxies from elliptical to more or less something that looks more spiral, because it's sort of like, imagine like a mixer going in circles and creating these unusual patterns. And eventually, for reasons that I'm going to be discussing in one of the future videos, these galaxies also start forming arms, the spiral arms that make this beautiful shape that you see right here, or right here, or right here. So these spiral arms are formed through another kind of action that's kind of common in many things that you even see in real life. For example, if you look down a drain of running water. But what's interesting here is that even after a few minutes of running the simulation, or I guess in game time 1.3 billion years, you can kind of see that a lot of the material first of all escapes this galaxy, but second of all, it becomes more stretched this way. It becomes more flattened even after a little bit. And this implies that this galaxy is actually going to start acquiring a kind of a inclination that's going to be related to those two supermassive black holes orbiting around one another. So their orbit, which you can kind of see right there, is going to create the inclination for this galaxy. And so eventually pretty much everything is going to be along this line. Right now it's going to take a while, of course, but with time it will get there. So what we're going to do is wait a little bit longer just to see what kind of shape this actually acquires at the end. But as you can see, creating a spiral galaxy that looks like a spiral galaxy is quite a challenge. As a matter of fact, this is maybe the 10th simulation I run in this game, and I'm still yet to acquire something that actually looks like this or like this. It's very difficult, and it does seem to require quite a lot of luck. So let's just wait a little bit and see what happens. And right now I waited almost 2 billion years. This is basically the time it would have taken that other galaxy to be created. And as you can see, mine looks nothing like it. Mine looks nothing like a spiral galaxy. And so that implies that the fact that the galaxy A1689b11 became a spiral galaxy means that they got really lucky. And that kind of shows because it's the first one we've seen that's so old and has a spiral shape. You can obviously try this yourself. If you don't have Universe Sandbox, the link for this game is in the description below. And see if you can create something spirally looking. And if you do, post a screenshot so we can all check it out. It is very difficult, it is very challenging, and it does require a lot of patience and probably a very powerful computer. So even with maybe hundreds of simulations, you'll probably get lucky maybe once, and even then it will be very unlikely to look like a real spiral galaxy, like this, with arms and everything. So creating this does require a lot of luck, a lot of patience, and obviously a lot of persistence. So the fact that our galaxy is this shape makes us very lucky yet again. So pretty much every major simulation that I've used often has one problem, and the problem is that it's very difficult for us to imagine motions of galaxies. As a matter of fact, I cannot think of a single simulation or a single video game even where galactic motion is presented at all. We're often presented with this. This is what we usually imagine when we think of a galaxy. Now, because of these spiral arms that we see in the Milky Way, we can kind of also imagine that it's actually spinning, and this is really as far as it goes with most video games and simulations and scientific articles. We don't really realize and never even think about, or mostly never think about, that this and also all of those other galactic spots that you see in the background are actually in constant motion and are always moving somewhere. Now, one day maybe Space Engine will have this capability of simulating the motion of all of these galaxies you see around us, but for now we're stuck with this still image, almost like a pause button of a video game. Here, or I guess sort of a video. Here, if I actually accelerate time, nothing really changes, nothing moves at all, which is very unfortunate. But there is a new study, and this study actually takes into account pictures that were taken for many years, and also analyses of pictures from other studies that try to estimate, based on redshift and based on radial velocities, where all of these galaxies are actually headed. And as a matter of fact, in this particular study and in the simulation I'm about to show you, you can explore, to some extent at least, where the Milky Way will be headed, where it's going to end up, and how our nearby galactic neighborhood might actually look like. Now, I'm just going to zoom out of here for a second, just to show you that this right here is what is known as our galactic neighborhood. So the closest galaxies to us are right here in this cluster, and the most well-known neighbor to us is Andromeda, at a distance of about 2.5 million light years right there. So this is the Milky Way, that's the Andromeda, and this is our neighborhood. There's about 56 galaxies here, most of them are small, only Andromeda, the Milky Way, and another galaxy known as Triangulum, which is right there, a little bit off away from Andromeda. These are the biggest galaxies that we know of. The rest are relatively small, also known as dwarf galaxies. So, if we were to actually imagine this as a motion, this is what it would look like. And this is based on the study and the analysis by an astronomer and the lead author for the study known as Ed Shea from University of Maryland. And I believe this particular simulation was actually made by Daniel Pomerade from University of Paris, Saclay in France. And this is essentially what it looks like. I can actually rewind this a little bit and press the play button, and you'll see that things start moving around. Now, every single ball that you see in front of you is a galaxy. Specifically, these are galaxies that we've already mapped and are nearby next to us, except for one ball. The biggest ball here, right there, the red ball, is the main attractor in this area, and this is actually Virgo cluster. This is where we're headed, and this is with about 600 trillion times the mass of the sun, and it's about 50 million light years away from us right now. But we are headed this way, and we are located right there where this little yellow spot right there. That's us right here, and this is the Andromeda galaxy. Now you'll notice that Andromeda and the Milky Way are actually slowly approaching each other as well. And in the next few billion years, they're actually going to collide and turn into one galaxy. And then they're going to advance here and join Virgo cluster and become part of a much, much bigger cluster as well. And actually, at the moment, as of today, we're still a little bit outside of the capture point from the Virgo cluster. But in the next few billion years, we're going to approach Virgo cluster close enough that it's going to capture us, and the motion of our galaxy will actually change. But I guess what's interesting about this particular simulation that you can totally just manipulate and move around. Oh, and by the way, the link for this is in the description below. The interesting thing here is that it really gives you a perspective of how all of the galaxies are actually moving. And they're moving around, and you can see that some of them are moving in the same direction, some of them are moving in a different direction, and some of them are kind of just doing their own thing. And this is how we define galactic clusters nowadays. When galaxies are moving toward similar direction, we define it as a local cluster. When big clusters move in the same direction, we define it as a supercluster. And in one of the previous videos, I've talked about the biggest supercluster we've discovered, and also our own supercluster known as Laniakea. And this is kind of what Laniakea looks like if you were to look at it. The Milky Way is right there, and our cluster is right there as well. And this is represented with something like hundreds of thousands of different galaxies. And all of this is, of course, in motion, and these lines denote the motion and direction of that motion. In other words, if you were to zoom in right here, and then zoom in here a little bit more, you would actually see something that looks like this. Now, what is really interesting here is that if you were to actually look at all of them over time, they're all moving towards something in our local area, and this something is known as the Great Attractor. It's something that's super, super massive, but we don't really know what it is. So eventually, once we join the Virgo cluster, which is in red, we're going to kind of all head toward a certain direction. Now, as you can see, this is actually before the Andromeda and the Milky Way collide, so this is maybe about 2 billion year period, and okay, maybe a little bit more. And eventually, in the next few billion years, all of these galaxies will actually form a relatively large cluster that we're probably going to be referring to as Virgo cluster if we're still around. And so just to give you the perspective of this again, so imagine all of those galaxies you see here moving around, and now we're going to return to Space Engine and kind of try to position things this way. So this is the Milky Way, that right here is Andromeda, and they're basically currently moving in this direction over there, and somewhere over here they're going to collide into a single object. Okay, maybe a little bit farther away, somewhere over there. So in other words, everything is currently moving this way. And if you look at it again in this simulation, you'll see that it's kind of headed toward Virgo supercluster, which is in that direction right there. So in other words, we're headed somewhere over here, somewhere in this direction. So in other words, all of these little spots are actually moving somewhere. But because things are so big in the universe, and because our galaxy is gigantic and other galaxies are even larger, it's hard for us as humans to imagine this motion, and it's hard for us to even realize that this is constantly moving somewhere at speeds of hundreds of kilometers per second. Well, that's kind of all I wanted to show you in this video, and specifically I just wanted you to understand that these things are moving that way. And one day, some of these galaxies will actually combine with each other and become even larger. And maybe, just maybe, our own Milky Way, because it's going to be so massive when it combines with the Andromeda galaxy, will reach a point where it's going to be extremely large as well. So I'm posting the link for this in the description. Do play around with this, check it out, and maybe even consider reading this paper, because it does show you some really cool facts about the motion of different galaxies. And also, if you want to actually know the names of these galaxies in this particular simulation, the page I posted also has a picture or an image that shows you the names of the nearby galaxies. Our own Milky Way right there in yellow, the Andromeda M31 is in red, and Virgo is the big spot on the right side, and other galaxies are marked here as well. Now we're going to be using Universe Sandbox Square to try to recreate this particular galaxy and to compare it to the galaxies that we're kind of more familiar with. Like, for example, this right here is a somewhat inaccurate, but I guess a relatively okay-ish representation of the Milky Way, with Sagittarius A star in the middle. The galaxy we're going to be talking about is known as Dragonfly 44, and it's actually also known as the dark twin of our own galaxy, because it has a very similar mass to the Milky Way, approximately 1 trillion suns in total. But here's the thing. About 99.9% of that galaxy is made up entirely of dark matter. In other words, you really wouldn't be able to see it. It would kind of look something like this. And there you go. Maybe a little bit more. I keep kind of erasing these Milky Way particles here, just so that it gives you an idea of what this particular galaxy might actually look like. There's actually a picture of it on the screen right now. It is practically invisible, and the only way the scientists discovered that it was made up of like 99.9% dark matter is because they measured the velocity of stars orbiting around that galaxy and realized that those stars were moving a little bit too fast. So the mass of that galaxy has to be very similar to the Milky Way, because as you may know, dark matter is actually what's holding our galaxies together. So here, let me just demonstrate this to you. Let's place the Andromeda galaxy right here in the middle, and you'll see that those red spots that you see on the screen are actually the dark matter. So if I were to accelerate time, you'll see that things start moving around, the galaxy kind of keeps for the most part together, and the dark matter is essentially gluing it all into one. However, if I go under power here and I erase all of the dark matter, things will just start falling apart. As a matter of fact, everything just flies apart. So dark matter is essential, but we still have no idea what it's made out of. All of the 4 major experiments of 2016 failed to discover the dark matter particle, so we don't really know what it is. We just know that it exists. So let's actually try to recreate Dragon 44 using Universe Sandbox, and we're going to do this from scratch by doing the following. We're going to place our first galaxy here, and it's going to have dark matter right there, but we're actually going to erase this part completely. We're going to just take this whole thing and erase it, just make it disappear, and then place another one right where the first one was, and do it again. And we're going to do this a few times, basically adding a huge amount of dark matter and erasing the huge amount of visible matter. Now, I think this is kind of enough, and what we're going to do now is make a lot of this visible matter just disappear by manually erasing it. And what I'm essentially trying to do here is just leave a trace of the visible matter. I'm basically manually erasing the extra visible matter, leaving just a tiny trace. So here, the galaxy known as Dragon 44 has something like over 100 times less stars in it than our own Milky Way. So this is exactly what I'm doing by essentially removing all of these highly visible stars and basically leaving behind just a tiny amount of them that will give this galaxy a very dim appearance. Alright, so let's see how this goes. This is definitely still a little bit too much, but let's just let this run and see if we can stabilize this galaxy, making it look somewhat realistic. And so here we go, matter and dark matter starts interacting, and for the most part, this galaxy is going to be kind of stuck all together because of the dark matter particles keeping it all in one place. And look at that, it's looking more and more realistic. Still a little bit too bright, but definitely not as bright as it used to be, possibly at least 20 times more dim. In reality though, this should be at least 100 times dimmer than our own galaxy, the Milky Way. And just to give you a comparison, I'm going to place another galaxy next to it just so you can see what the actual galaxy looked like originally. But for now, let's just make it stabilize itself and create the replica of Dragonfly 44 that I just renamed right there. It's the black hole in the middle of it. Alright, so as it stabilizes itself, let's actually maybe talk a little bit more about why this is kind of an interesting finding and how this was also discovered. So the scientists who discovered this particular galaxy actually knew about this a long time ago, but they decided to measure the motion of the stars for about 34 hours. They measured the motions of stars and realized that these stars were moving way too fast. And for these stars to actually maintain their orbit, for them to move that fast, there's got to be so much more matter than was actually visually observed. And when they realized that they didn't see any matter in the vicinity of this galaxy, they kind of concluded that it must be the dark matter that's holding it all together. That's essentially how we also explain why in our galaxy stars move a little bit faster than they should as well. On top of that, discovering such a galaxy creates a bit of a question. How was this ever formed? How did such a galaxy come to exist? This obviously has no answer yet because we don't really know what dark matter is, and obviously we don't really know enough about creation of galaxies to answer this question, but nevertheless, this is essentially a pretty cool representation of what Dragonfly 44 looks like. Now, let me just give you a comparison of what the real Messier 85 looked like before, and I'm going to place it just next to it, I guess, right there. So it's still maybe a little bit too bright, I guess, but a lot dimmer than it was originally. And so this is what it used to be like, and this is what it is now. So maybe I should have erased a few more of the actual stars for it to be a little bit more realistic. Now let's actually just erase this for a second, because what I want to do next is I want to actually remove all of this dark matter, all sort of in one press of a button, and see what actually happens to Dragonfly 44 if it had no dark matter holding it together. And as you can imagine, it's not going to last very long. So let's look at the years here. We're going at about 3 million years per second, and suddenly all of the dark matter disappeared. And look what happens. The entire galaxy, within a few million years, flies apart and leaves the supermassive black hole all by itself, with maybe just a few stars around it. So essentially, without the massive amounts of dark matter that you saw, there's absolutely no way this galaxy could actually hold itself together. And that's Dragonfly 44, the galaxy that we officially confirmed and I guess rediscovered back in August of 2016. A pretty cool discovery, and definitely puts a lot of new mystery and opens a lot of new questions for the idea of dark matter, what it is and what it is not. Maybe one day we'll discover, but definitely not yet and not today. Anyway, thank you so much for watching. Hopefully you learned something about our galaxy, our universe, and about Dragonfly 44 as well from this video. And if you did, don't forget to subscribe, don't forget to share this video with someone who enjoys learning through video games and someone who actually wants to learn cool things about space, sciences, and other things as well. Now let's actually go ahead and place a few more galaxies just for fun, and let's see how they interact together, with the most massive being M32 that we're going to place right here. And let's see what happens if we once again erase all of the dark matter and let them spin around without any dark matter left. Let's see if any of them actually survive. So if we move this fast, we're not going to get to those galaxies very fast because we're going to a distance of several million light years. So we need to accelerate in space engine and we need to go far, far away. The first place we're going to is actually a galaxy by the name of Whirlpool Galaxy, also more officially known as Messier 51, because this was the 51st object discovered by the infamous French astronomer Messier. He classified these objects as nebula. He basically thought these were objects that were relatively close to our own sun, but in reality they were much, much farther away. So let's actually cheat a little bit and go to M51 slightly faster. And so here we go. This is the Whirlpool Galaxy as it appears in Space Engine, but to make it more beautiful, let's actually increase the luminosity a little bit just so you can see what it may look like if you were to look at this in a telescope. And so here we go. This is the M51, also known as NGC 5194. It's a very, very active galaxy with lots and lots of stars being made and also lots and lots of stars being destroyed as well. The bright spots that you see are basically the so-called stellar nurseries where stars are being actively created. And in the last 17 years or so, we've detected at least 3 very bright supernovae, meaning that at least 3 stars were destroyed and created more material. Now, this is a very common type of a galaxy. This is also known as a spiral galaxy, similar to, of course, Milky Way. And this galaxy, because it's so similar to ours, allows us to study these spiral galaxies in a lot of detail and actually teaches us about our own galaxy as well. There's about 77% of all galaxies that are this type of a galaxy. And they're very, very common, but this one is very close and very bright, so we can study it very, very well. Anyway, let's go to the next one, and this one has a slightly different, more gentle name, the Sunflower Galaxy. Also known as M63, also named by Messier. This is the 63rd object. And this here looks slightly more unusual. You can probably guess that it's called Sunflower Galaxy because of the unusual spots that you can kind of see in some locations, and these are actually due to really tight spirals inside the arms of this galaxy that create these really unusual sunflower patterns. The brilliant glow actually is generated by these newly formed, very, very bright, very powerful blue-white giant stars, and they're basically creating these unusual patterns that you can kind of see. Now let's come from the other side just so you can see it a little bit better. This is the Sunflower Galaxy. Anyway, next one has an ominous name, the Black Eye Galaxy. More officially known as M64, more unofficially known as the Evil Eye Galaxy. You can probably guess why. The ancients were kind of scared of this, because it looked like something is staring at them. So this particular galaxy has lots and lots of space dust right here in the middle that very likely is there because of a collision with another galaxy and basically the absorption of another galaxy. In other words, this galaxy swallowed another galaxy completely. And the center here actually rotates in the opposite direction, which also implies that something was swallowed by this galaxy and something that was spinning in the opposite direction. So this is probably one of the most evil-looking galaxies that we're going to visit here, and we're going to talk about this galaxy in more detail in one of the future videos. Anyway, let's go to something a little bit less evil-looking, maybe something a little bit more unusual. We're going to go to a galaxy known as the Sombrero Galaxy. That's right, this is probably the largest, the most massive Mexican hat in the universe. This galaxy right here, unusually named Sombrero Galaxy because of the way that it looks from the side where we're looking at. Basically, it kind of looks like a big Mexican hat. Maybe a little bit more so if I change the luminosity a little bit. and maybe this is what the scientists usually see and what they refer to as the Sombrero Galaxy. Now, this is a very, very massive galaxy, up to 800 billion masses of the Sun, probably the most massive Mexican hat in the universe. But kidding aside though, it is a very, very massive place, with most mass obviously being dark matter, but nevertheless quite a lot of mass being various stars of various types. And if you were to come from the top here, this is what it would look like. It's a very interesting looking ring galaxy, also known as NGC 4594. And speaking of unusual Mexican objects, the next galaxy on the list is actually named Cigar Galaxy. And Cigar Galaxy, also known as M82 or Messier 82, doesn't really look like a cigar at all, at first at least. Now I'm going to try to make it look cigar shaped, or at least show you the appearance of what seems like a cigar by repositioning myself to a location where you would see it maybe a little bit better. So it sort of is how we see it from Earth. This is actually what it does look like from Earth, Earth being completely behind us right now. And even though it's kind of hard to see the actual cigar, it does look like something or someone is puffing some smoke here. Now, this particular galaxy, also known as M82, is actually, let me just point at it again, a place with very, very high star birth rate. Basically, a lot of stars are being actively created here at all times, up to 10 times more than in the middle of our galaxy, the Milky Way. And because of this, this is the kind of a shape and the kind of a brightness that it creates, making it look very, very unusual and giving it this very unusual irregular shape with a lot of dust right here, making this galaxy have slightly different colors. It's actually a little bit more red here than it currently appears in Space Engine. So this is probably one of the more unusual irregular galaxies we're going to visit in this video. And this is probably one of the more unusual places in nearby galactic space to us as well. And this is what it looks like on the inside. Welcome to the cigar smoke. Alright, let's go to the next galaxy. This one might be familiar to you because it's actually appeared quite a lot in my previous videos as well. A galaxy by the name of ARP 188, more commonly known as the Tadpole Galaxy. You're going to see why it's called Tadpole in a second. Here it is. Here is the beauty. Look at how beautiful this galaxy is. Now, this long tail is what gives this galaxy its name. And this long tail was probably created because of another galaxy that passed by nearby and kind of stretched this tail, making it really look like a tadpole from a distance, with a head and a tail. Now, Tadpole Galaxy is very well known to the astronomers, and it's actually very, very beautiful if you can find it in the telescope. And as you can see, it has another tail sticking out here. And what makes it really, really beautiful is, of course, the fact that this tail stretches for like 300,000 light years. So this beautiful protrusion is very, 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 very long. Imagine if our galaxy that's about the same size as this would have this long stretching tail moving behind it. And we can actually go inside of it and check it out as well, just to give you an idea what it feels like inside this beautiful tail. And we might want to enable some stars here just because we want to see these stars as well. So there you are inside the Tadpole Galaxy's tail. This is what the center looks like. And the last galaxy on the list, not surprisingly, is our own galaxy, the Milky Way, because it does have a very unusual name as well, and actually for a reason. Now, we don't really see our own galaxy, because obviously we are inside of it, but Space Engine allows us to see our galaxy from the outside, and we get to actually experience what it might look like if we were to go outside of it. Now, we know that, or we used to think at least, our galaxy had two massive spiral arms. But then in 2013 we discovered that there's actually at least 4 arms. There's 4 arms here that we now are almost confident are all massive areas of star creation, star formation. And one of such regions where our Earth is located, this region right here, is known as the Orion's Arm. This is essentially one of the stellar formation regions, with one of the more commonly known areas known as Orion's Belt and Orion's Nebula. All of these are areas where a lot of stars are being formed, including very likely at some point our own star, the Sun. And a long time ago, when ancient Greeks looked at the skies, they actually saw something that reminded them of spilled milk. And they named that particular region of space the Milky Way. This is actually what it may look like in a space engine. So here is that Milky Way that the Greeks saw, and they named it that. And then, with time, we named the entire galaxy the Milky Way. And as a matter of fact, the word galaxy itself has the word galactose in it. Galactose is also milk. So all of the galaxies are technically dairy, or have dairy names in them. And that's because back then, Greeks thought it looked kind of milk-like. And every good adventure starts on our planet Earth, so we're going to start from here. And let's actually talk about what Andromeda used to be known as. So, as a matter of fact, if I look into the sky right there, I'll see that you can kind of see the Andromeda. As a matter of fact, this is one of the few objects you can easily see with a naked eye in a dark enough location without using any binoculars, without using anything really. And to be honest, this is actually the farthest object you can see with your naked eye. So if you were to look in the night sky, this right here is the only object you can see without a telescope that's about 2.5 million light years away. Ridiculously far. And let's actually try zooming in here using the telescopic function in the game, just to see what it would look like if you were to use binoculars or a telescope to look at this. And so this is essentially what the scientists back in early 19th and 20th century saw when they looked at Andromeda. And it used to be known as Andromeda Nebula. So they actually thought that this is just another nebula or possibly a star that's being formed with planetary objects orbiting around it that was part of our Milky Way galaxy. This actually was a common knowledge until about 1923. This is when things really changed. A person by the name of Hubble, who has a telescope named after him, discovered that one of the stars in this beautiful galaxy was something known as a Cepheid variable. I've actually talked about this concept previously, and you can check out the video on the channel, but let's actually just talk about what this meant for Hubble. Discovering a Cepheid variable in Andromeda meant that he could now look at it and try to estimate its distance, because Cepheid variables allow you to basically use the star variability period, or basically changes in luminosity in comparison to the actual luminosity that you see, to try to estimate the actual distance to this object. And what he's discovered was mind-blowing. He discovered that this distance was in millions of light years. This was actually the first time they discovered an object that was so far away. And anyway, so let's actually go to Andromeda Galaxy and let's take a look at it and try to find that elusive supermassive black hole at its center. So we're going to accelerate toward it at several thousand light years per second, and we're going to go outside of our own galaxy and basically visit the Andromeda. So some of the more interesting things about it is that, first of all, this galaxy is about twice as massive as the Milky Way. Its total mass and its number of stars is at least twice as big. So there's about 1 trillion stars in the Andromeda, with only about 400 billion stars in the Milky Way. It's also about twice as big. It's about 225,000 light years across. But in every other sense, as you'll see in a second, it's actually very similar to the Milky Way. As a matter of fact, it looks almost identical. So it's a spiral galaxy, and it's a barred spiral galaxy, meaning that it has a bar going through the middle of it, which you'll see in a second as soon as I come close enough to it. And we're going to turn our view around a little bit just so you can see the bar that's somewhere right here-ish. I think it's somewhere right here. It's kind of hard to see it here. It's a little bit more visible on our own Milky Way. And interestingly, just like the Milky Way, this galaxy has companion galaxies around it. So there's actually two that are right here. This one is known as M10, and this one here is known as M32. And these two galaxies actually experienced a bit of a bullying from the Andromeda, because billions of years ago, when they came close enough, it took a bite out of them. It took a huge chunk out of them and combined it into itself. And because of this, this galaxy doesn't really have very straight spiral arms. Its spiral arms are kind of wiggly because these two galaxies actually disturbed Andromeda galaxy when they were close enough to it. But there are actually 24 companion galaxies around the Andromeda, and you can kind of see some of them orbiting around there. They're smaller companions. Our own Milky Way has about 16, whereas this one has 25. And there's actually another large galaxy in the vicinity known as the Triangulum galaxy, and all three, Triangulum, Milky Way, and Andromeda, form what's known as the local cluster. In total, there's actually about 54 galaxies in our local galactic cluster, and there's the Triangulum right there, but we're going to be mostly focusing on Andromeda. And let's actually go into the center and try to look for that supermassive black hole. I may actually have to disable some of the magnitude here, mostly because it's a little bit too bright. So let's go and look for some kind of a cluster of stars, maybe right here, and try to see if this might contain the supermassive black hole in the middle of this galaxy. Now, the interesting thing about the center or the central region of this galaxy is that it doesn't just have one very bright core, but it seems to contain two. And after years of study, the scientists discovered that, one of those cores, one of those very bright objects, is the supermassive black hole that's about 25 times more massive than the supermassive black hole in the center of our own galaxy, known as Sagittarius A star. So this one here is about 100 million masses of the sun, and I'm going to try to look for it by doing the following. We're actually going to maybe cheat a little bit. We're going to select Andromeda and basically look at this arrow right here and go toward the direction where it's pointing. So it says it's this way. I think it's possibly in this globular cluster right there in front of us. It's got to be inside of that thing. So we're going to go and find that 100 million masses of sun supermassive black hole that doesn't actually have a name. It's just known as the Andromeda's supermassive black hole. And one day this is actually all going to become part of our own galaxy as well, because you may have watched the video where I talk about the collision between the Andromeda and the Milky Way. In about 4.5 billion years, the Andromeda galaxy is actually going to collide with our own Milky Way and combine into it, creating very, very large elliptical galaxy that we might actually refer to as the Milkdromeda, because they're going to become part of one. And it's going to become the most massive, the largest possible galaxy in our local cluster. Alright, so the arrow is telling me that it's right here, and I think it's this bright, super bright object right in the middle. So just to check, we're going to accelerate time. And if we see stars orbiting around this super bright object right there, that's got to be the supermassive black hole. So let's go closer to it, and let's check it out. And maybe take a look at the stars as well. Yeah, the Andromeda Galaxy is actually moving toward our own Milky Way at a speed of about 140 kilometers per second. And obviously it's going to accelerate when it comes closer, but right now it's moving toward us very, 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 very fast. And so, just as I mentioned before, this particular central region has two very bright nuclei. So this is the first one. This is the actual black hole, known as M31 central black hole, because M31 is the other name for the Andromeda Galaxy. And I'm not sure if this is actually correct. I don't think this is a correct mass here, because it's technically 100 million masses of our own sun. But the actual central region has two of these very interesting bright regions. So one core is right here, and in reality there is actually another core somewhere right here formed by all of these thousands of stars orbiting around the black hole. And as they orbit around the black hole, some of the stars remain here in the apogee, or the farthest distance of the black hole, and create this very, very bright object. So if you actually look at this with a telescope, what it looks like is a very bright object here and a very bright region here. So this is why Andromeda is known as a dual nucleus galaxy. It has two very bright nuclei in the middle. And so let's actually go a little bit closer to the super massive black hole in the middle of Andromeda, slow down time a little bit just so it looks a little bit nicer, and maybe just go on the inside as well. We're going to go inside of it and make the Andromeda galaxy and the entire universe disappear behind us. And so here we go. Boom, it's all gone. Anyway, so that's really all I wanted to say in this video. I just wanted to teach you a little bit about the Andromeda galaxy, about its properties, about its history, and the importance of the discovery of this really beautiful Cepheid variable star known as V1 in the Andromeda galaxy that basically changed the understanding of the universe. Before Edwin Hubble discovered V1, we thought that all of the stars in our night sky are basically part of the Milky Way. But he realized, and he discovered, and he showed that that was not true, that there were other galaxies out there and that the universe was actually a very, very large place. And I guess before we finish this video, let's actually return back home and take a look at all of this as it looks from Earth, just to remind ourselves how far away this actually is, how much of a distance we actually had to travel to get here. And of course, remind us of the fact that not only is this actually far, but the light that we see coming from the Andromeda galaxy is actually 2.5 million years old. So everything that we see today is basically the history of Andromeda that basically started way, way before humanity even existed. So this is actually how impressive all of this is. And let's zoom in onto the central region here and maybe see if we can discover that globular cluster that we just came from, where we saw the supermassive black hole. And I think maybe it's this one right here, with the bright region in the middle being the supermassive black hole. So first, let me start by showing you the picture. So right here, you're looking at various types of so-called ring galaxies. Now, these are essentially galaxies that seem to have a ring around them. These are very, very massive usually, and the current speculation is that a lot of these galaxies have very young blue and white stars forming on the outskirts and making this kind of a beautiful ring. And essentially, this is what creates this kind of an effect, and nothing seems to be happening in the center, either because there's a lot of really old dark stars, or because everything for some reason moved to the outskirts. Now, the actual most prominent theory right now is that the ring galaxies are essentially formed in a way that, well, basically in this way. Let me just show you instead of trying to talk about it. Basically, you have two galaxies that collide, and one of them is smaller than the other. When a smaller galaxy passes through the bigger galaxy, in the center you'll get like an empty space. On the outskirts you get a bunch of stars. That's the current most prevalent theory explaining these particular beautiful ring galaxies. But some other astronomers think that maybe it's just formed because there's a very large accretion disk on the outskirts of these really massive galaxies that essentially starts producing these new stars that then obviously create so much light and such a beautiful ring. So two theories. One is that it's a collision of two galaxies, one small, one big, and two is that maybe it's because of this accretion disk that is there for some reason. And this is actually the galaxy that this person sent me. This is the Cartwheel galaxy, a very beautiful, very well-known galaxy that has this really cool look. It actually does kind of look like a cartwheel, and apparently it's a lot more massive than we thought. What you see here is actually, it's not showing you the dark side of this galaxy. It doesn't show you the darker stars and specifically the black holes binary systems. Basically, there's a lot of binary black hole systems that surround this galaxy, and we can see them in the X-ray, and they actually show up on this particular picture because this is the X-ray imaging, and you can kind of see that there's quite a lot of these really massive, beautiful objects. Now, why are we talking about this? Well, because in one of the previous videos, when I was talking about dark matter, this is what we've talked about. We've taken a look at the galaxies, if they actually had dark matter in them. Specifically, this is a pretty good example. So here's a typical galaxy. Actually, maybe not this particular simulation. Let's actually use this right here. This is a little bit better because it's already accelerated as well. I'm going to pause it for a second. We're going to zoom out. And so here we have these two galaxies that are kind of spinning around each other. We're going to maybe decrease this a little bit. And they're held together by the red dots, which are sort of the representations of dark matter. This is essentially the theory behind dark matter right now, is that this is how the galaxies are kept together. But then what I did was I went into power here and pressed the magical button that removes the dark matter. And see what happens? They actually turn into ring galaxies. Are you kind of detecting where I'm going with this? Let me try this again. I'm going to go into this, zoom in on this lonely galaxy right here in the middle. It kind of looks galactic enough. And we're going to basically, well, first of all, let's accelerate this. And we're going to remove the dark matter. And you'll notice that it actually will once again turn into a ring galaxy, which is absolutely fascinating. Now, the fact that he saw this before I think a lot of scientists did is pretty amazing. I don't know if this is actually what's happening. This is totally a speculation on my part. I've never read a single paper that tried to explain it this way. So maybe right about now, I can maybe pause this or decelerate this a little bit. And so what we have here is we have the central part that sort of does obviously have a lot of stars orbiting the central supermassive black hole. You can kind of see them if I zoom in a little bit more. And this is because they actually, they're not moving fast enough to escape this part. But then these stars are moving fast enough. And before they were being held by the dark matter. And now there's no more dark matter, and so it actually kind of, sort of, from a certain angle, if you squint your eyes, totally looks like a ring galaxy, or possibly a cartwheel galaxy. Like, this is totally a cartwheel. If this is not a cartwheel, I don't know what a cartwheel is. But anyway, so I thought that was an absolutely amazing observation on his part, and I actually wanted to ask you guys, what do you guys think? Does this actually make sense? I'm totally going to tweet this to some of the more famous astronomers out there that actually do know a little bit more about dark matter than me, and maybe they will have an answer for us, because I honestly think that this person is kind of on the right track. Maybe, just maybe, this is actually how these unusual galaxies are formed. Maybe it has something to do with dark matter either somehow disappearing or somehow losing its potency, or possibly maybe something else is going on there. Maybe there's just some kind of effect we haven't really observed yet, or haven't really studied yet. But anyway. So Galactic Merger in Universe Sandbox looks absolutely incredible. Especially if you have VR, you can actually check this out, because it just blows your mind. This is such a beautiful event. Now, I'm going to actually demonstrate a few more simulations, and one of them is made by NASA that looks really, really, really cool. And I really wanted to show it to you because it's something that you don't see very often. And the event that you see right here is essentially the formation of large galaxies similar to the Milky Way. So what you're observing is a simulation of smaller galaxies, and I guess some big galaxies, kind of interacting and absorbing each other's mass, and essentially creating a bigger and larger galaxy that will eventually become spiral, similar to the Milky Way. Now, this is a simulation by NASA, and you can actually find it in a link in the description below. But you kind of see that it looks pretty cool. It looks really awesome. Everything is spinning really fast. And it shows us that galaxies seem to be created from smaller, less massive galaxies, and basically merge into large things that look like our Milky Way. That's kind of what we think happens. But then something else occurred in 2017. We actually saw this right here. This was taken by a telescope in Antarctica, and this is a picture of two very massive galaxies, one here and another one here, merging together. But on top of that, they're actually inside a very, 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 very large dark matter halo, the size of which we haven't really seen before. So there's two problems here. One is, of course, the dark matter, but that's another story, because we don't really know why so much dark matter is present in this location. But the other one is the two galaxies themselves. First of all, this is like observing two very large Milky Way and Andromeda-like galaxies colliding early on in the creation of the universe, maybe about 700 million years after the universe was created. We didn't really think that these galaxies existed back then. We actually were under the impression that only smaller galaxies, similar to the ones you see here, were around. So we didn't think that such massive galaxies even existed. So that's kind of already a redefinition of our understanding, because that means that early on in the creation of the universe, there already were these really massive galaxies that collided with each other, interacted with other galaxies, and absorbed them, and then basically became more and more massive. So this is what is going to happen here. We're going to have a very large and massive supergalaxy. Now, the other interesting fact is that, well, first of all, this would explain why we actually did find some tremendously huge and massive galaxies out there that just defy explanation. Like, for example, the biggest galaxy in our universe that we've discovered so far, known as IC 1101, about which I've talked about maybe about a year ago, is so massive and so large that it's just, there's no explanation for how it was formed. And so, having found these two merging galaxies, we can now kind of possibly predict, or understand at least, what actually possibly happened. So maybe this is the beginning of that supermassive galaxy IC 1101, because now that it's actually more massive than other galaxies around it, it will be able to absorb more and more mass, grow exponentially, and become tremendously big. But unfortunately, in this simulation that we started just now, things don't look as good for the supermassive galaxy that we wanted to create. It doesn't look as supermassive or as big as I hoped it would. But I guess if you actually put more and more galaxies here, which we can do right now, to basically try to simulate the situation, and unfortunately, as you can see, it suddenly slowed down because I have so much dark matter everywhere. So let's try this again. Let's remove the dark matter and try to run this at any kind of speed. And you'll see that even in this particular simulation, it's very unlikely that we're going to create a large supermassive spiral galaxy. It's going to be really hard. I've run so many simulations where I tried to combine galaxies together, and I think maybe in 1 out of 100 there was something that resembled a spiral galaxy, so they're kind of hard to create. And so we're gonna wait a little bit and see what happens here, but chances are we're not gonna create anything as spectacular as you saw before. But before I actually go on, I wanted to tell you about the paper where I found all of this, and this is also in the description below. This is the paper known as Galaxy Growth and Massive Halo in the First Billion Years of Cosmic History. The paper is actually kind of interesting to read, so if you are into this kind of stuff, check it out. The link is in the description below. And the NASA simulation is from the Goddard Media Studios, which basically has a lot of really, really awesome videos that simulate various galactic formations and galactic collisions. And there's quite a lot of them you can check out. There's also some other really awesome videos on this site, but these are the ones that apply to this topic right now. But anyway, so going back to our formation of galaxies, as you can see, nothing really changed here. And it's probably going to kind of be in this form for a very long time, and I believe these other galaxies are actually moving away now because there's nothing holding them together. These ones are also floating apart. So our supermassive galaxy creation didn't really succeed yet again. I mean, it is supermassive and it is kind of blobby looking. I guess in this case you would call it an elliptical galaxy, although not yet. But it doesn't look as I wanted it to look. It doesn't have the spirals. Now, in comparison, the most supermassive galaxy we've discovered so far, IC 1101, is about this big in comparison, or actually even bigger. I believe it's at least 100 times bigger in size to our own Milky Way. So it's a galaxy that is elliptical. It's made up of smaller galaxies, and it contains so much mass that it's unbelievable. It's hard to kind of describe. And just to show you an example, if you've never seen this galaxy before, this is kind of what it looks like compared to the other galaxies. And this is in the space engine, so you can see these tiny galaxies next to it kind of look tremendously tiny. So this is IC1101, and here right next to it, if we were to zoom into this particular galaxy, you would see that it is tiny in comparison. So there is IC1101 in front of it. And I've actually talked about this giant and even recreated it in Universe Unboxed in one of the previous videos, so do check it out on the channel. So anyway, so that kind of is the end of the video. I wanted to show you the new mystery of the formation of the galaxies. We still don't really get how exactly these giants form. We don't really get where and how most of the dark matter came from and how it influenced the formation of the galaxies. But most importantly, we just realized that this formation of galaxies that we thought was kind of the standard doesn't seem to be the standard. It looks like there are galaxies out there that have been formed in some other ways, way faster than we expected them to form, and it looks like we need to redefine our understanding of the universe yet again. Well, anyway, this is what our supermassive mass looks like now. Doesn't look like anything galactic, I guess, but it is a galaxy that contains about 10 other galaxies. So, first of all, let's establish some basics as we're escaping from our beautiful Earth, and as we're moving across our own galaxy relatively fast, faster than the speed of light. So yeah, nothing in the universe can actually move faster than the speed of light. This is something that Einstein has established in his general theory of relativity a long time ago, and most of his theory is actually absolutely correct. So nothing, no object can move at a speed faster than the speed of light, even though we're currently doing so in space engine. But that doesn't include space itself. Universe itself can actually expand faster than the speed of light. In other words, as I move away farther and farther from Earth, we actually know that space itself expands outwards. Space moves away from us, and it moves away faster and faster. The farther you are from Earth, the farther you are from the center of observation, the faster space moves away from you. Now, it's not as fast as you can see right now. This is mostly just a simulation. But if I were to go to a location approximately 1 megaparsec away, or 1 million parsec away, which is something like 3 million light years away from us, at that location, the space itself moves away from us at approximately 70 kilometers per second. In other words, let's actually just simulate this by selecting Earth and moving to a location about 73 million light years away from our Earth. So somewhere around here, we're going to just stop completely. So here's our Earth. Somewhere over there, we're going to zoom into it and just to see our galaxy for one more time. There's the Milky Way. Maybe not the best view from this particular location, but we can actually pan around just so you can see it a little bit better. Earth is somewhere in the middle right there. At this particular location, even if we're basically stopped completely, we're actually moving away from Earth approximately 70 kilometers per second. And that's because of the so-called Hubble's law. This is a law that was discovered by the scientist by the name of Hubble approximately 100 years ago, and he was able to prove it. He was able to show that the farther away you are from the center of observation, the faster things move away. And so this, of course, implies that the farther away we move from the center of observation, the faster space expands away from that location. So that also means that if we were to go to a location approximately 4,300 megaparsecs away from here, basically what we would call the edge of the universe, at that location, light would actually, or not just light, but everything would actually recede from us at approximately the speed of light. And so let's go there right now. So this is going to be approximately 13-ish billion light years away from our Earth, that is right there in the center. So right now this is just 1 billion, And let's go to 13 billion. So we're going to basically reach this edge of the universe. And things there will be expanding a lot faster. And so we're almost there, and here we go. So somewhere around here, maybe a little bit farther. I guess Space Engine doesn't simulate this super accurately, but right around. So somewhere around right here, this is where, if you were to stop completely, you would be receding from Earth at approximately the speed of light, even if you were completely stopped. Now, because our universe is expanding in every direction from us, this means that this kind of forms a sphere around our location, and this is what we would call the Hubble sphere. And no, this doesn't actually violate Einstein's theory at all, because space itself can expand as fast as it wants to. As a matter of fact, there was actually time a long time ago when space expanded so fast that we have a name for it. It's called inflation. It basically instantly expanded to a tremendous large size. But since then, it actually stopped. But it is still expanding, and it is still actually even accelerating and increasing its expansion speed. And our only explanation for it so far is that there's something called dark energy that's causing it to accelerate. Anyway, this is another topic, of course, because right now we're just talking about these galaxies right here in this vicinity that are at a distance of about 4.3 billion parsecs away from us, that seem to be actually moving away from us at the speed of light. Now, would we be actually able to see galaxies that are slightly farther away? So, like for example, this galaxy right here, and this is a galaxy that's very bright, is actually beyond the Hubble sphere. It's beyond the so-called visible location, visible light location. So in other words, this is moving away from us faster than the speed of light. So the light that's coming off it may actually never reach us, because it's actually moving away, at faster than the speed of light. But we actually do see them. And we see them with time, because as it so happens, the Hubble sphere itself expands with time as well. And at some point, the Hubble sphere will become larger, and when it becomes larger, the light that escaped those galaxies that are moving away faster than the speed of light from us will enter the Hubble sphere and eventually reach our planet Earth, and eventually we'll be able to see it. Now, there's actually a really good explanation of this on Veritasium's channel. He made a video about it back in 2013. But what I wanted to talk about in this video is actually just the kind of a visualization and kind of an explanation for a lot of this other stuff using Space Engine. So we know that many of these galaxies, like for example, this galaxy right here, is emitting light toward us right now. So let's actually maybe come closer to it so we can see it in a little bit more detail. And here it is. This beautiful procedurally generated galaxy with a funny name. So this galaxy is outside of our Hubble sphere. In other words, the galaxy itself will never actually be inside the Hubble sphere, and it's currently moving away from us at a speed that's faster than the speed of light. But the light that escaped billions of years ago will eventually enter the Hubble sphere, and will eventually be able to see what this galaxy looked like billions and billions of years ago. So this is actually very, very unusual, because a lot of the light that we see today from about 5 billion years ago and beyond was actually emitted by objects that used to be past our Hubble sphere. So this at some point will also be visible to us, even though currently we cannot see it. And all of this light, when it reaches us, is going to be extremely redshifted. It's going to be very, very redshifted. We might not actually even be able to see it very well, because it's essentially going to be not this color at all. It's going to be very, 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 very redshifted and appear almost in infrared. And also, this brings me to my next explanation about some of the galaxies that are right at the Hubble sphere itself. So there's actually a location right here, somewhere in this region, approximately 13.8 to 14 billion years, light years away from us, where a galaxy in this particular region will actually slowly kind of disappear from the visual light. It will become so redshifted that it will start appearing in infrared and not in visible light. And so if you were to stare at a certain location, like for example, maybe this galaxy right there, if we can maybe see it a little bit better. So here's a random galaxy that I kind of selected. If we were to kind of skip staring at it over and over and over, at some point, because it's moving away from us, it would actually slowly fade away into the infrared. So we need to use infrared telescopes to actually see it, which is actually very unusual. And this is one of the reasons why our night sky is actually so dark. Technically, if all of the stars in the universe were still in the visible region of space, our night sky would be extremely bright, but over time, many stars actually faded away past the Hubble sphere, and actually past the so-called particle horizon. This is actually the limit of where we can see things even today. And this particle horizon expands to a diameter of about 93 billion light years across the universe. So it's approximately 46 billion light years away from us that we can actually see objects still. So for me to really reach the visible limit of the universe, I have to go really far away, and I'm going to show you how far away it is. So in Space Engine, at about 24 billion light years, this is where the observable universe kind of ends. But if we move to approximately 45 billion light years from us, this is technically the limit of the particle horizon. This is the limit of where we can still kind of detect things from. And these things are essentially extremely red-shifted. They're barely even visible to us at all. And unfortunately, in Space Engine, it's kind of hard to simulate this, but let's just reach that location right now. And so somewhere around here, in this complete darkness, this is essentially the limit of us seeing things. Even though it's kind of invisible at this point in Space Engine, in real life we can still kind of detect certain things from this location, because they emitted light so many billions of years ago, and because their light has entered our Hubble sphere a long time ago. So now we're going to go back to our Earth. I'm going to zoom back to it, fly through the entire visible universe, and I guess invisible universe, and appreciate how far away things really are in space. And here we go, we're coming closer and closer to Earth, zooming past trillions and trillions of galaxies, and now we're back to Earth. So let's actually start by escaping our own planet Earth and of course our solar system, just so you can actually see where this close galaxy is located, and you'll actually be surprised how close it is. And so as we actually start moving through the galaxy here, you'll notice that we're about to escape it, and you'll basically get to see the Milky Way from a distance. So there is the central region of the Milky Way. Our planet Earth is somewhere over here, and we're actually not going very far. The way for us to find one of these galaxies, one of the closest galaxies to us, is to actually increase the magnification here, and you'll start actually seeing a lot of new things. You'll actually start seeing a lot of globular clusters, and I'm going to fly through some of them just to kind of explain to you some of the new findings. So in the last few years, we've used something called 2MASS, which was a kind of an infrared analysis to discover quite a lot of things that were previously invisible to us. This was an infrared analysis that discovered all of these globular clusters you see right here and right here and right there, and many of them actually form something known as monoceros ring. Now, monoceros ring is a kind of a well-studied subject. It's basically a ring that we're going to recreate in one of the future videos that forms a very interesting pattern around our galaxy, making our galaxy a lot larger than we previously thought. As a matter of fact, in 2015, which is only a year ago for me, we discovered that our galaxy is not actually this small, it's about this big. It's about almost like twice the size, meaning that our Earth is actually somewhere in the middle of the galaxy, as opposed to being in about 2/3 away from the center. And what we've also discovered is that this monoceros ring actually is formed by possibly a destruction of another galaxy, or possibly by some kind of a very interesting interaction of matter inside the galaxy that we still haven't really been able to explain. But what is interesting is that during that 2-mass study, we also discovered a really interesting, very small, but relatively close galaxy that you see right there. It's literally hugging our own galaxy, and this particular object is known as CMA Dwarf, also known as Canis Major Dwarf Galaxy or Canis Major Overdensity. Now, the reason why it's actually known as overdensity is because we're not 100% sure that this is actually a galaxy just yet. We've recently discovered it, we're still studying it, but we kind of are going to assume that it is actually a galaxy because it sort of does look like a dwarf galaxy and because it sort of behaves like one. Now, what we know for sure is that this particular galaxy is slowly being absorbed into the Milky Way, and basically it's going to disappear at some point, and in the last billion or so years, it already lost quite a lot of its mass. Quite a lot of those globular clusters that you saw a few minutes ago are actually, used to be at least, part of it. But today we know that it's kind of there, it's very close to our own galaxy, and it's actually not very far away from the solar system that we live in either. It's only about 7,000 light years away, so it's actually closer to our solar system than to the center of the Milky Way. So Earth is actually right here. And this right here is CMA Dwarf, and the central region is right there. So it's only about 7,000 light years away, which is actually not very far. Earth is closer to this galaxy than it is to our central black hole. Now, previously, there was actually another galaxy that we thought was much closer to us, and I'm going to show it to you in a second. It's going to appear somewhere right there. There it is. We actually thought that this was the closest neighboring galaxy, known as Sagittarius Dwarf Spheroidal Galaxy, also known as SAG-DSPH. This was basically a galaxy that consisted of 4, or I guess it still is a galaxy that consists of 4 globular clusters. And in this case, we actually discovered this back in 1994, but we now know that it's very likely to be not the closest one. So this particular dwarf galaxy is about 10,000 light years in diameter, and it's about 70,000 light years away from Earth. And this galaxy will too at some point be very likely absorbed by the Milky Way and basically disappear completely and become part of our own galactic spiral disk. But we're not talking about that galaxy. We're actually talking about this right there. So let's zoom into CMA Dwarf and briefly discuss what's inside and what we know about it. So it's actually hidden from us by all of the galactic dust and galactic clouds, so you would never be able to see this with a regular telescope. But using infrared telescope, we can definitely actually see not only the actual galaxy, but a lot of its parts as well. Now we're going to actually go into the middle and see if we can discover the central black hole, because I would like to actually see if we can maybe find it. Although, considering the fact that this is actually a very large galaxy consisting of about 1 billion stars, it might be kind of challenging. Now, this particular galaxy is classified as the irregular galaxy, and it's about 25,000 light years away from our solar system, but over 42,000 light years away from the galactic center. It's somewhat elliptical in shape, and this galaxy is located in the region known as Canis Majoris, which is also sometimes known as the dog. And here we're actually possibly approaching the center of this particular galaxy, because I think maybe inside this globular cluster there might be a black hole. Now, so let's go inside of this and try to find the central black hole while we talk a little bit more about what this galaxy is all about. So the fact that this galaxy exists and the fact that we know that Milky Way is absorbing it slowly kind of gives us a proof, or I guess shows us that many different galaxies do grow by absorbing their neighbors, specifically smaller galaxies. And this one here is about 1% of total mass of the Milky Way. And it's actually going to be absorbed in the next few billion years completely. It's going to disappear and become part of the Milky Way. Now, my guess is that the central black hole might be somewhere in here. So we're going to inch our way toward the center and try to discover and see if it's actually here. And while we're approaching this black hole, which is hopefully somewhere here, let me just also mention that not everyone believes that this is an actual galaxy. There's actually quite a lot of researchers that think that maybe, just maybe, this is just a part of the halo of the Milky Way. Maybe these are just stars that are there in a kind of a globular constellation as well, that basically make it look like an actual galaxy, but in reality it might be just a natural formation. I have a feeling this right there might be the actual black hole, because I'm getting really close to it. So maybe this is actually it. So let's get a little bit closer and take a look at it, and maybe even go inside. And there we go, look at that. So you can actually see the orbits of all of these stars orbiting around what seems to be a central, very bright region, which can only be one thing. It can only be a black hole. There's a bit of a slowdown there because I think the game was loading all of these stars, and we can actually decrease the magnitude now, because we don't need to see so many stars. As you can see, if you increase the magnitude, you almost see all of the stars that this galaxy has, whereas if you decrease it, it becomes more manageable to go through the simulation without your computer basically crashing. And so here we go, we're approaching the relatively small supermassive black hole, and I guess that's a funny play on words, small supermassive. It's small compared to other supermassive black holes, but it's definitely still a supermassive black hole that you're going to see any second now, because we're definitely getting closer and closer to it. And I don't really know the exact size of this black hole, but there it comes. Very bright accretion disk, and we're going to stop right in front of it just so that you can actually see it. And there it is. So let's actually slow down time here so you can see the accretion disk orbiting a little bit slower than it was orbiting before, and we're going to approach the center. Here it is. This is what it looks like inside the CMA dwarf galaxy, and this is what it's like on the actual event horizon of this particular black hole. Not that we'll ever be able to get here, because this would be scientifically impossible, or very improbable. Anyway, so that's basically the center of this galaxy. We're going to escape it now, take a look at it again from a distance. But I also wanted to mention that we now also know that a lot of the other globular clusters that we were aware of previously might have actually come from this particular galaxy, and a lot of them are available in Space Engine. Like, for example, if I were to find an object known as NGC 1851 that's located right there about 17,000 light years away from us, and I'm going to try to make it a little bit more bright so you can see it. This object may have actually come from here. It may have actually come from this particular galaxy when essentially the Milky Way disrupted the galactic formation here, and that part kind of got separated from the rest of the galaxy. So a lot of these globular clusters may have actually originally come from the CMA dwarf galaxy. So that's what we know about it so far. All of this is still a bit of a speculation, but it's basically the closest explanation we have to how these globular clusters ended up so far away from our own galaxy, the Milky Way. And that's, of course, the CMA dwarf. It does take a while to load, mostly because I'm actually using an add-on to try to recreate this galaxy, because originally this galaxy is not in Space Engine. And you can actually find this mod and download it yourself from the forum board of Space Engine. Now, before we finish this video, I actually am going to go back to Earth and show you where exactly this galaxy is located. So let's return to Earth and look behind us and actually discover where you can maybe possibly see this galaxy if you were to actually have a very powerful infrared telescope and you really wanted to find it. So here is our own solar system. Here is our beautiful planet Earth. And now we're going to turn around, look into the area of where Orion's belt is. We're going to increase the magnitude and wait for the galaxy to pop into view. And there it is. If this is Orion's belt, that's where you would find the beautiful CMA dwarf irregular galaxy. It's about 25,000 light years away, or about 7,000 kiloparsec away from us. So astronomers often scan our skies looking for different new phenomena to discover, and one such phenomena happened to be this very large, extremely cold dark matter galaxy known as Crater 2. But what's really interesting about it is that it's actually part of our subgroup of galaxies close to us, And as a matter of fact, it's one of the few galaxies orbiting the Milky Way. But what's even more surprising is that it's actually relatively large and very, very massive. So anyway, let's go to Universe Sandbox. So here's our own Milky Way galaxy. Our sun is somewhere over there. It's kind of sticking out. And this is a galaxy that's pretty well known to us, obviously, but it at the same time still has a lot of mysteries. But what we've discovered is that there's about 57 smaller galaxies that are within about 1.4 million light years away from the Milky Way. And we've discovered quite a lot of them orbiting around our galaxy. There's actually some very well-known ones, like, for example, Large Magellanic Cloud and Small Magellanic Clouds. And these don't actually orbit around our galaxy. They're moving a little bit too fast. And then there are some that actually do orbit, like, for example, Sagittarius Dwarf Elliptical Galaxy, about which I've talked about in one of the previous videos, is in orbit. But then came the discovery of Crater 2. The thing about Crater 2 is that it is massive in comparison to some of these other dwarf galaxies. And the other thing about it is that it's actually pretty close. So let me show you how close we're talking about. Okay, in galactic terms it's close. In human terms it's still kind of far. Now, to represent the Crater 2, because it's full of dark matter, we're actually just going to use a black hole. And specifically, we're going to use Sagittarius A star black hole because the total mass of Crater 2 is about 4.4 millions of suns. And the mass of Sagittarius A star is about 4.3 millions of stars, so it's kind of almost exactly the same. So here we're going to go to a distance of approximately 380,000 light years away from Earth and basically from our own galaxy. And that's approximately somewhere over here-ish. So somewhere over here-ish. I'm going to place Sagittarius A and we're going to rename it to Crater 2. And now we're going to add a few stars to it because it does have stars. It is a galaxy, but there aren't that many. As a matter of fact, what it has around it moves really fast. And the actual black hole in the middle is probably not very large either. But it does have a lot of really unusual properties. Or not, I guess not unusual properties, but the properties that basically define this as a dark matter galaxy. So let's just place some stars here, just so that we can actually give it some galactic-like appearance. And this is going to be our miniature model of Crater 2. So what we have discovered about it, having found it completely by accident, is that being so close to us and being so dark, it's very likely that it's been there forever. We just haven't seen it, and it's been in this region for forever as well. But we're not looking for the right thing, and specifically here we're not really looking for the gravitational interactions, which is how we were able to accidentally find this galaxy. And the mass of this galaxy is, or makes it, one of the most massive satellite galaxies to the Milky Way. It's more massive than the Small Magellanic Cloud. Basically, it's somewhere between the Large and Small Magellanic Clouds in total mass. But it's almost invisible. It's very dark. It will be impossible to see it with a home telescope. You would need a specialized telescope to see it. But if you were to look at it from Earth, if you were to actually look at this galaxy from Earth, its size would be almost double of the Moon. That's how big it is. So it's a pretty large galaxy, but just completely dark because of its content, which is essentially just mostly dark matter. And we've actually found, at least in the last decade or so, quite a lot of these dwarf satellite galaxies, making total 57 now. And some of them include very small, very dark, very chemically enriched, but also mostly dark matter dominated galaxies. And some of these are actually just like this. They're basically a few stars, a lot of dark matter, and a lot of mystery in there. We don't really know exactly what else is going on and how they were formed, but we know that these galaxies were partially responsible for the creation of our own Milky Way, and a lot of their gas kind of get captured by the Milky Way as well. But because this galaxy is so massive and also because it's so large, as a matter of fact, its radius, well, this is not a good representation of its total radius. Its radius is about 4,000-ish light years. So it's actually somewhere around here in size. This is how big it is. So I'm going to actually just enable orbits for a second, just so you can see how big it is. This red circle represents the actual size of this galaxy in relation to the Milky Way. So it's pretty big. It would definitely be very visible if it was a lot brighter and contained a lot more stars, but instead it's very dark because, of course, it's just dark matter, about which we still don't really know much. We just know that it exists. And so all of these parameters make it fourth largest satellite of the Milky Way, and also one of the most massive. Now, because of all of this, it also is the most extreme low density galaxy that we found in the neighborhood. It basically has very few stars. There's barely any stars at all. And the stars that are here probably have complete darkness in their night skies. There's probably not a lot of things in between. If you were to look at the dark skies, basically you would just see the other galaxies. You would see the Milky Way, but you wouldn't really see many stars because there aren't really that many to begin with. And the reason that we know that it's basically all dark matter, or mostly dark matter, is because the stars that we've discovered on the outskirts of this galaxy move way faster than they should. So something is definitely keeping them together, and these stars that are basically orbiting somewhere in here and there and there and there, all of these stars move really fast, and some of the outlier stars move at speeds of like 4 kilometers per second, which is way faster than they should be moving based on the total mass of this galaxy. So unfortunately, that's actually all we know about Crater 2. We know its size, we know that it's there, we know that it's mostly dark matter, and we know that it's very large and very massive compared to some of the other similar galaxies nearby. In terms of anything else, we're still going to be studying quite a lot and trying to discover more about this unusual dwarf galaxy, and maybe even discover some unusual new parameters about the dark matter because of this galaxy. And anyway, so that's all I wanted to talk about in this video, and hopefully you learned something from it. And if you did, don't forget to subscribe, share this video with someone who enjoys watching space videos, and come back tomorrow to learn something else. As you can see, now that I've disabled the orbital parameters, this galaxy is barely even visible. It's just a tiny little dot in the middle of other dots. And that's essentially how it really is. And that's why we haven't seen it until 2016. So creating a galaxy is actually not a very easy business. As a matter of fact, even today we don't really know exactly how the galaxies were created early on, because we don't really see any creation of any galaxies anywhere in the universe using telescopes. So as a matter of fact, all of our theories so far are based on observation of galaxies that have already been created and using computer simulations similar to what I'm using here. And so far, all the theories that exist are not particularly accurate in predicting the way our universe looks right now. But one of the more prominent theories is the so-called bottom-up theory, where basically the way it predicts the creation of the galaxy is that a long time ago, there were these clumps of matter very similar to what I have right here. Basically, a matter that compacted itself into a large chunk that kind of started to accumulate on and orbit around a central point, which in this case is a central supermassive black hole. And as they started to orbit around it, they started to accumulate into larger and larger chunks and created stars and basically galaxies as we know today. This theory is not perfect, and it does lack a lot of accuracy and doesn't really predict the rotation speed of the galaxies or their size very precisely, but it's one of the theories that scientists still kind of follow and try to basically prove. But nevertheless, we're going to actually try to use one of these theories to kind of create a completely new galaxy from scratch, and I'm going to also demonstrate and show to you how you can do it yourself. So let's create a new simulation here. And we're going to start by placing some kind of a black hole, a very large black hole. In this case, I believe it's a black hole that has 1 million masses of the sun right in the center. And let's actually name this galaxy something cool, like, for example, and I'm going to name it Anton's Galaxy because, well, I couldn't really come up with a better name for the lack of energy of thinking and creativity on my part. Anyway, so moving on. What we're going to do now is we're going to place two types of clumps or clump matter around this black hole. The first one is going to be in form of brown dwarfs. Or specifically, basically large planets, or I guess you can call them almost stars, that are large enough to look like a planet, but behave more like an unborn star. So in this case, I'm going to be using a brown dwarf by the name of 2M1207. This is one of the ones we found in the last few years, and it's type M8 red dwarf that's only about 26 masses of Jupiter. It's going to represent a clump of hydrogen. So basically this is hydrogen that's been collected into one large chunk. We're going to place quite a lot of them around this system with a black hole in the middle, and there you go. There's basically like something like over 100 of them here. Now, they will start colliding at some point, and they will start creating matter and eventually even creating stars. But to accelerate this process, and also to make this a little bit less clunky, let's just remove this as well. Ooh, wrong button. There we go. To make this a little bit sort of more realistic and make this a little bit quicker, we're also going to place a ring of matter just to make this even more interesting and realistic. And I'm going to choose Saturn ring right here. Let's change the mass. So here I'm going to place about 2,500 particles that are going to be total mass of about 100 suns. We're going to keep the texture by default. It's going to basically be kind of almost invisible. And the only thing I'm going to change is the distance here. And let's place it at a distance from about 0.3 astronomical units to about 1.2 astronomical units around this black hole in the shape of Taurus. So let's add one, and let's actually maybe add one more in the shape of the ring as well, just to make the collisions happen a little bit quicker. And so here is our Anton galaxy, or Anton's galaxy. That's completely brand new. This is basically a baby galaxy. It's an undeveloped galaxy. It's completely devoid of any stars. It just has matter orbiting around it. Now, what we're going to do is just wait. We're going to accelerate time here and wait for things to happen. And if the theories are somewhat correct, stars will start to appear relatively soon. And it actually already kind of looks cool. To me, it looks like basically an undeveloped solar system that has a black hole, a supermassive black hole in the middle. Now, the game might start slowing down here because, as you'll see in a few seconds, there will also be a bunch of smaller fragments created from all of the collisions and possibly from approaching the black hole too close, as it will actually shred things. But for now, there's really nothing happening. It's just matter orbiting very peacefully for about 4.6 days. And some time has passed. And there you go. You just noticed that all of the fragments have disappeared because the first star has been created and changed the luminosity of this particular area. So now we have our first baby star. Let's actually name it that. Let's call it Anton Baby Star. There's our first beautiful tiny star. You can kind of see it right there. And we're going to just wait for more to... Oh, there you go, second star. We're going to see for more to happen, for more to be created, for more stars to occur. And so now let's just see the magic, or I guess the science, happen in front of our eyes. So this is a completely newly born galaxy. It's going to be essentially developing itself. It's going to be creating more and more stars. And in this case, we refer to these galaxies as blue type because you'll notice that after a few possibly months of game time, all of these stars here will become blue and the galaxy will become completely blue. As the galaxy evolves and as it dies down and the stars are no longer created and less stars being developed, it changes color to red, and it's also known as the red type of a galaxy. For now, it does look kind of reddish because there's only 3 stars now, but it will change the color. So I'm going to kind of stop talking for now and let you observe the magic. Or the science. I keep calling it magic. It's really not magic. It's science. And as more and more collisions occur and as more stars are born, you'll notice that some of them have even become a little bit bigger than their partners, than their neighbors. Like this one here is quite large already. And what this will eventually lead to is very large blue stars, and also supernova. So we might even witness a supernova sometime soon, because some of these stars will collide and some of them will reach very high masses and will basically live out their lives to the point where they'll explode and create even more dust, even more matter, and of course new materials and new things like iron, silicon, nickel, and so on and so forth. So elements that do not yet exist in this system. Right now, ooh, look at that, something just happened. It says it's a nova remnant. I think this star actually approached the black hole a little bit too close and fell apart into little fragments. But yeah, there will be a lot of new materials created here, and there will be a lot of really new cool things. And there's our first supernova, and look at that. The galaxy has suddenly become blue. It lit up instantly, and this supernova basically changed everything. I think it added a lot of materials and a lot of mass to all of the other stars. It also warmed up some of the things and has basically mixed up things and added new elements to the galaxy that used to be made up entirely out of hydrogen and maybe some helium. Now, however, it has a lot of metals and a lot of other cool things. So let's keep rolling this simulation and see what happens after basically a few months of game time. But right now, this is what we would call a blue-type galaxy. A galaxy with blue stars, or white stars, very bright, very hot stars that are going to go supernova and create a lot of material. And as you can see, my game is kind of slowing down because there is so much stuff happening here, it's not even funny. And the second supernova occurred because two other stars probably collided and reached their supercritical mass. Although technically this would be called a red luminous nova, but in this situation it might actually have been a supernova as well. Now, just to make this run a little bit faster, I think I'm going to actually get rid of these two supernova. I'm going to delete them, and I'm also going to erase... Oh, there were 3 supernova. I didn't even know that. Actually, there were even 4. And I'm also going to erase all of the fragments and particles that have been created from all of these collisions. And just like that, as soon as I removed all of the particles, I think another supernova occurred. Well, that's cool. Anyway, so let's keep running this. I would like to actually see how this develops with time and what actually happens to this galaxy later on. So right now, it's definitely what you would call a living galaxy. All of the stars are still young, new things are being created, new materials are being created as well. There's a lot of mixing going on, a lot of things are being turned from hydrogen and helium to heavier metals, heavier materials, and all of the new elements are basically being created both inside the stars and through supernova that you just saw. Some stars are still red, but as they grow in size, they'll become blue and white and create more supernova. So right now the galaxy is super active. A lot of supernova are happening, a lot of stars are being created, quite a lot of mass is still orbiting around the black hole, and a lot of it hasn't really combined yet. And this is essentially what you would call an adolescent galaxy. Basically, it's a teenager. It's a very active teenager that is spewing out a lot of tantrums in forms of supernova. But then there will be adulthood, and eventually this galaxy might even reach something that you would call death. Okay, well, we're not really talking about the death. Like, it's this thing right here doesn't really have life, and yes, it's not really going to die in the same sense that one day all of the people on Earth will die, but it does have something akin to existence. So, galaxies can be divided into really 2 types. The blue cloud and the red sequence. Blue cloud refers to something I've covered in the previous video where I've created a new galaxy that became very bright, very blue, and had a lot of stars that have been created. A red sequence, however, would be something similar to what you see right here. So this is a miniature galaxy that contains nothing but red dwarfs that are still alive and white dwarfs that are basically stars that used to be like our sun and lived out their life and became really, really tiny, but very dense pieces of matter. And in the middle you have the supermassive black hole. These types of galaxies are basically in a sense dead, because no new stars have been created, and because these galaxies one day will become very dim, very dark, and possibly completely disappear. Now, we don't really call them dead though, and we don't call this dying, but we call this quenching. So this galaxy quenching is essentially the kind of a period in galaxy's life when no more new stars have been created, and where all of the stars are basically kind of slowly living out their lives, and all of this one day will disappear. But galaxies are unlike life on our planet, can actually resurrect and start producing stars again. Now let's talk a little bit more about all of this by creating a few galaxies and just talking in general about the idea of galaxy quenching, or I guess galaxy death, and the idea of resurrecting galaxies by various means. So first, let's actually talk about how this whole quenching thing happens. Now, one of the most common ways for quenching to occur is when a bigger galaxy or a more active galaxy, like for example this one right here, interacts with a smaller or less active galaxy and essentially neutralizes its hydrogen. There's several ways of doing that. One of them is by essentially, and let me see if I can actually recreate that here, essentially sucking out all of the hydrogen from the other galaxy. We're gonna see if we can create this effect by basically making this particular black hole ridiculously massive and essentially making all of the hydrogen kind of suck into this other galaxy. Okay, well, that's not exactly what I was trying to create. This is a little bit more extreme, but you get the idea. So when the hydrogen from the other galaxy disappears, the older or the smaller galaxy will not be able to produce any more stars. The other thing that can happen is a galaxy that has a nucleus that basically has these two super active jets that propel a lot of energy toward these two locations. And if by some chance there is another galaxy located right here, right in the middle of this jet. Okay, that totally missed the actual spot where I was aiming, but what I'm trying to do here is place it right here, right in the jet. So if this galaxy is right in the jet, the actual jet will neutralize a lot of nitrogen and once again prevent the star formation. And this by itself actually has a name. This is actually known as galactic strangulation. Basically, when one galaxy strangles the other galaxy, preventing it from forming new stars. And it happens quite a lot in our universe, and it's actually been observed many times. So there's basically two mechanisms. One is through these really highly radioactive and very highly energetic jets, or any other means that basically make hydrogen unable to combine and create new stars, and the other through sucking of that hydrogen into the black hole or into some kind of a supermassive, very highly gravitational body inside another galaxy. But for a typical galaxy that you see right here, basically this is a miniature version of a typical galaxy where stars can be very different and have quite a variety of life in front of them. Anything from blue stars that will go supernova really soon to red dwarfs that will live for trillions of years. Strangulation may not occur, but they will still one day reach this so-called red sequence and essentially quench themselves. They'll basically die, including our own Milky Way and including our neighbor, the Andromeda. Right now they're in so-called green stage. Basically, they're not really dead yet, but they are slowly reaching the stage where no new stars will be made maybe in a few billion years. But until that occurs, they will obviously be creating some stars. Now, for a galaxy to be quenched, basically it has to have no more hydrogen left to produce new stars, and all of the supernova that may actually occur in this particular galaxy would have to be not powerful enough, or I guess not dense enough, to produce any more new stars, or maybe all of them have to have already initiated and no supernova capable stars should have been left in that particular galaxy. So essentially what I'm doing right now is I'm quenching or killing the galaxy I've just created. I'm making all of the blue and white stars go supernova. I'm essentially getting rid of any way for this galaxy to create new stars. And after a few billion years, this is what's going to be left. A galaxy filled with nothing but white dwarfs and red dwarfs. Basically stars like our sun that lived out their life and stars that will slowly live out their lives for trillions of years. There's also going to be a lot of black holes, a lot of neutron stars in there, but a lot of them will not be as visible, so for the most part this galaxy will be relatively dim and relatively hard to see. But something else can actually happen to resurrect this galaxy, and that something else usually is a collision between two galaxies. When Andromeda and Milky Way collide, they might be almost red sequence, they might be almost dead. However, the collision that you're about to see here will actually initiate two things. First, a lot of the leftover gas from both galaxies might mix up and create a lot of energy as it sort of creates friction, a lot of particle collisions, and this by itself might actually initiate another stage that will create or basically resurrect the two galaxies and create another temporarily blue cloud stage where many new stars will be made from the gas that has just mixed up right here. Now, no stars will collide, but the gas will actually clump together and possibly create a lot of new stars. And at the end of this collision, we'll actually end up with an elliptical galaxy, very likely known as Milkdromeda, because that's the only name we came up with. We came up with so far, and that's the name. Because that's the only name we've came up with so far for this unusual collision that will occur something like 4.5 billion years from now. But of course, until that happens, both galaxies, both Andromeda and the Milky Way, will essentially use up all of their stellar gas, or interstellar gas that is, and create all of the possible new stars that they currently are capable of creating. And once that's done, both of them will very likely end up as red sequence galaxies that will essentially look very dim, have no new star formation, and for the most part will slowly dim away into non-existence. And if you are okay with waiting a few more billion and trillions of years, you'll eventually reach a stage where pretty much all of the galaxies will look very similar to each other. At some point, all of them will be barely visible. As you can see right here, there's maybe a few white dwarfs, but for the most part, this entire galaxy consists of mostly black dwarfs, black holes, and possibly a few neutron stars here and there. It is very dim, it is almost impossible to see, and this is as quenched of a galaxy as you can kind of imagine. So what you see in front of you is a recreation that I made previously where I was trying to play around with the idea of galactic tides or the effects of the central black hole and the central region of our galaxy on various objects in our solar system. But we're actually going to recreate this from scratch, and I'm going to talk more about the details and why we're actually doing this. But before we start all this, let's actually briefly define what tidal force or a galactic tide actually represents. So any kind of a tide is essentially a tidal force experienced by any object, like for example right here, there's Earth right here, that's actually is experiencing tidal forces from the center, from the galactic center that's right there. We are familiar with tides on Earth, we see them anywhere there is water, and usually those tides are caused by either the moon or the orbit of the moon around the Earth. And so in this case, the moon is right there, and because it's right there, it's actually pulling on Earth, so the water level right here is going to be raised compared to water level on the other side. And we also get the same tidal effects from the sun as well. So because Earth is actually orbiting around the sun, the side that's the closest to the sun also is experiencing tidal effects as well. But they're actually very minuscule. But because our sun is orbiting around the galactic center, it's also experiencing tidal effects from that. So as the sun actually orbits around the galactic center that you're about to see in a second, so there's Sagittarius A star, as it orbits around this region, it's also experiencing galactic tides from essentially the center of the galaxy. And these tidal effects are very small, but they can actually affect objects in our solar system. As a matter of fact, if you were to compare the galactic force from the sun, from the moon, and from the galactic center forces are very minuscule. And so if the tidal forces from the moon would raise the water level on Earth by about 10 meters, then the tidal forces from the sun would raise it by about 5 meters. Whereas the tidal forces from the galactic center would only raise it by a tiny number of about 1 picometer, which is actually smaller than the size of an atom. So the actual forces are quite insignificant. But the thing is, when it comes to objects on the outskirts of our solar system, like for example things like comets that I just added right there, or things like asteroids in the Kuiper's belt, these objects actually might get quite a lot of influence from the tidal effects. And let's actually see if we can maybe simulate this a little bit, because they're actually far enough away from the sun to be affected by any kind of perturbations. And also over time, over millions and billions of years, even these tiny effects of tidal forces might actually influence various objects in our solar system. And so specifically, a lot of scientists today believe that the tidal forces from Sagittarius A star and from the central galactic region might actually have caused a lot of different comet collisions and asteroid collisions in the past, and they may also have created up to 90% of all comets that we have today. And so as you can see, even with just a little bit of time, these various asteroids have already started to change their orbital paths a little bit, even with just a little bit of the gravitational effects from the central black hole. But what I wanted to do here is actually find out if there is any significant effects from tidal forces that can possibly even influence our solar system in other ways. So let's actually create a new simulation with Sagittarius A star in the middle and possibly a few other smaller black holes just kind of orbiting around it, sort of just to represent the galactic center. We're going to place them in a completely random order. They're going to just orbit everywhere, just to add a little bit of effect to the gravitational forces here. And so now what we're going to do is we're going to place a few suns with Earths orbiting around them, and I'm going to try to investigate two things, two potential hypotheses that have been kind of unanswered still. And hypothesis number one is actually going to try to answer a simple question. Could have the effects that we observed in orbits of objects like Ares and Sedna have been caused by the galactic tide and not Planet 9 that is still being searched by the scientists? Could it have been done by something else? In other words, if as you can see here, this is the Planet 9 simulation. The current hypothesis is that those really extreme orbits of various Kuiper belt objects has been caused by the hypothetical Planet 9. The other question we're going to try to answer is in regards to some asteroids that we've discovered in our solar system that have a very peculiar orbit as well. And specifically, we're talking about orbit that is retrograde and very highly inclined, sort of like this. And the third question we're going to try to answer is in regards to our own solar system, or just actual planets in our solar system that all seem to have a bit of an inclination. So if you were to actually look at all of the major planets here, they all seem to have just a little bit of inclination. Specifically here, there's like 3.4 for Venus, 2.5 for Saturn, and even 1.3 degrees for Jupiter. So this inclination has never been explained. The only explanation that we had so far is that maybe Planet 9 has actually caused that as well. And maybe there's something that's causing the actual orbital plane to slightly incline in comparison to other objects. But it's also possible that this could have been also caused by the galactic tides. So like, for example, Venus has 3.4 degrees and Mercury has 7 degrees, and it's not really explained yet, at least scientifically, and we only have speculations. But we're going to find out if it's possible to actually create this kind of inclination using a simulation with a central galaxy and basically a miniature solar system. So let's do it again. We're going to place a bunch of suns here, and they're all going to have relatively similar parameters. First sun is going to be in circular orbit, second sun is going to be in circular orbit as well, third sun is going to get a little bit of an inclination because we want this to be just a little bit different and more, a little bit more realistic, because our actual sun is not perfectly in a circular orbit around the galactic center. Then we're going to place another sun with a slight inclination as well, and basically we're now going to place Earths orbiting around them, and we're going to kind of investigate various galactic tidal effects on these Earths. So we're going to place Earth in completely perfectly circular orbit around the first sun, completely perfectly circular orbit around the second sun, and the other suns as well. Now the distance here is a little bit different, but we're just going to keep it relatively similar for now. So let's actually name them as well. And the first sun is going to be known as the circular sun. This sun right here is also circular, but we're actually going to maybe give the Earth that orbits around it a little bit of initial inclination, just so it has just some inclination, and we'll see how it actually changes later on. And we're going to name this sun Inclined Earth. The third sun will get a slightly eccentric Earth. We'll see how that changes with time as well, and we're going to name this Eccentric. And the last sun will get a bit of everything, and so it's going to be both eccentric and inclined. And actually, I think I'm going to add one more sun, and this is just going to be another circular orbit sun. And this time we're going to place Earth in a more realistic sort of orbit. Basically, it's going to be orbiting sort of perpendicularly at about 90-degree inclination right here. So kind of like this. This is what it's going to be doing. And now that I've actually set up all 5 of them, I'm going to kind of see what happens after a few orbits around the central black hole. Now, I think a lot of them are smoking mostly because they are relatively close to the sun. But I think with time they should stop smoking and start basically orbiting. Now, the reason I wanted to actually change the parameters for all of these different objects is because I wanted to take a look at various graphs here. So we're going to actually accelerate time a little bit so that the actual planets are orbiting around the sun, which I think they're doing right now. Let me just double check if they're actually orbiting. Yeah, I think they are. And as they orbit around the sun, they should start getting various changes in their parameters here. So maybe not all of them will have a stable orbit. I think actually this one here just flew away. But a lot of these other objects are going to stay in orbit around the parent star. I think this one is definitely orbiting, so is this one, so is that one, and this one as well. But I'm guessing it's because I placed the Earths a little bit too far away. Maybe I should place them a little bit closer so that we actually have a slightly better visible orbit. And let's try this again. So this time they actually have their parameters reset, and they're a little bit closer to the sun at about 10 million kilometers. So as you can see, this one here was supposed to have only inclination, and what I wanted to actually do is to look at the graphs here and how they actually change as the suns orbit around the central galactic region or central black hole. But if I were to actually click on inclination here and set it up as a separate graph and also click on eccentricity, you would see that both of them would start kind of going up and down a lot. As these stars orbit around the galactic center, the galactic tides will actually start influencing both the inclination and the eccentricity of every single Earth that we've created. And it will be more visible with certain stars, because like if a star has a very high eccentricity to begin with and it actually comes closer to the galactic center, it will obviously have higher galactic tide effects. And so these effects right here are actually the galactic tide effects that you're observing. So you can see that this particular Earth that's actually orbiting the inclination star was supposed to only have high inclination. But in reality, even though it actually has increased its inclination, it's also increased its eccentricity to about almost 1% now. And it's going to stop, not stop, but continue doing this for quite a while. Let's actually take a look at other graphs as well. So this was the inclination Earth. Let's take a look at the circular Earth. And I think the circular Earth lost its Earth again. Oh, that's not good. Let's replace it again. We need to try to make a stable system here. We're just going to place it a little bit closer. And so here we go. So this was a circular Earth a second ago. This is going to be its inclination graph, and that's the eccentricity graph. And as you can see that right away, even though it was a circular Earth with circular orbital parameters, basically it was in plane and it was completely circular, almost right away it acquires a bit of eccentricity and a bit of inclination, and it will start going up and down quite a lot. And with time, this will change quite dramatically. Now, you may ask yourself, so, how many orbits has our sun actually done around the galactic center? And the answer to that is, well, approximately 25. One orbit takes just over 200 million years, and our sun is about 4.6 billion years old. So it's somewhere more than 20, possibly less than 30. And so within those orbits, it's experienced a lot of galactic tides, ups and downs from various parts of the galactic center and from various interactions with other stars. And because of that, it obviously had some of the eccentricities and some of the inclinations changed within itself, within other objects of our solar system. So for example, Venus and Mercury have a high inclination, and it was possibly done by the galactic tides, not by the so-called Planet 9. But you know what, for now it's just a speculation, so we don't really know. We're gonna leave this for now. We're gonna check out some other ones. And I believe actually many of them have lost their Earths because they weren't really in a stable orbit. And as you can see, even the Earth that was placed perpendicularly starts changing its eccentricity and inclination quite dramatically, and quite periodically as well. So the galactic effects will basically affect every single object in our solar system, no matter how far away from the sun it is, including of course the sun itself. And so here the eccentricity is slowly increasing, and the inclination keeps going up and down, but I guess more down than up. And let's actually maybe investigate the other suns as well. And here, this one is the eccentricity sun. This is the one that had high eccentricity already, and the eccentricity here has increased even more. The inclination is also increasing, and actually very, very, very fast. So no matter how you place these Earths, no matter how you place the suns, the galactic tides have a very, very, very big effects. And the last Earth I'm going to take a look at is the Earth that already had a bit of eccentricity and a little bit of inclination. And I just wanted to kind of see what the actual patterns will emerge here with time. So here we go, orbiting around the galactic center. And as you can see, as we orbit around it, there's going to be a bit of a repetitive pattern. Now, it's not really predictable. It's kind of actually hard to predict, mostly because there's other interactions with these black holes and other stars in the system. But with time, you'll see that the inclination will kind of return to its original value, then possibly drop down, possibly increase. So there's always going to be some kind of an effect on this planet here. And so we're just going to wait a little bit and make it orbit around the sun just to kind of see what kind of a pattern emerges here. So this is probably the most realistic representation of our sun, except of course that the actual Earth should be orbiting more perpendicularly. But we're just going to let it run for a little bit just to see what kind of a eccentricity and what kind of inclination pattern emerges. Now, so there's the galactic center in the middle. There's a lot of craziness going on, but as you can see, this is essentially the inclination curve. So it started at about 8 degrees, it slowly increased over time up to about 15 degrees after one orbit, and now it's at around 18 degrees, and it keeps increasing now. Whereas eccentricity keeps going up and down periodically. So eccentricity is not changing too much, but the inclination definitely is changing, which is really a kind of an important finding here, because this suggests two things. One is that galactic tides could actually have caused the planets in our solar system to change their inclination quite dramatically. So maybe that's why Mercury's inclination is about 7 degrees. Two is that possibly the asteroids that we have, like for example, the two asteroids I've talked about in one of the previous videos that have a very unique inclination and very unique orbital path, may have actually been created because of this as well. Maybe they were influenced by the galactic tides, and their inclination was increased to about 110 degrees because of that. And three is that maybe the effects we're observing from various dwarf planets, like for example Eris and Sedna, are actually not Planet 9, but are actually caused by the galactic tides as well. Now, all of this will be discovered in the future when we do a little bit more research. But for now, this is actually what I wanted to talk about in this video. I wanted to show you how strong the galactic tides are and how much they might be actually causing in our solar system, including, of course, various potential collisions that could have actually wiped out the dinosaurs as well. So the asteroid that hit our planet 65 million years ago may have actually been redirected to our planet by nothing else but a galactic tide.